Okay, great. We are going live. Huh? Okay, great. We are going live. Hello, everyone. Welcome, everybody, to the split learning on distributed machine learning, SLDML’21. So quick announcements. The workshop website is splitlearning.github.io/workshop.html. There's a Slack channel that we are running. It's very active with all sorts of Q&A and discussions. It's called Split Learning. It's on this website, pandemic.mit.edu/Slack. All right, so we had quite a packed agenda yesterday with a lot of good keynote talks and several research talks. We also had 2 modules of the Code Your Own SL, Code Your Own Split Learning hands-on training workshop yesterday. The 3rd module is going to be today. So this is the schedule for today, and the schedule is in more detail on the website. Another interesting call, we also shared this information yesterday. We are putting out a call for kind of a very detailed survey on advances and challenges in split learning. So since we have a packed 2 days of sessions now, what we will do is we will reach out to you in a few weeks, especially the speakers and their collaborators and co-authors, so that we will set up some breakout sessions so that we form the original, the main outline of the paper. Once we have that, we're going to divide into breakout sessions and work collaboratively and integrate it into a common overlay file. So there's that. And yeah, I'm kind of very excited to invite our 3rd keynote talk speaker, Supriya Chakraborty. He's from IBM TJ Watson Research, and he's been working on very relevant areas for a while. So let me stop sharing screen so that Supriya starts sharing the screen now. All right, Supriya, we can go ahead and do the screen share.
Can you all see my screen now?
Yeah, looks great.
Great. So thank you, Praneeth. And hello, everyone. Thanks for attending my talk. So in this, I'm going to present 2 things. So my talk is divided into 2 segments. In the first segment, I'm going to talk about the threats and vulnerabilities that arise when we deploy federated learning. And in the second segment, I'm going to briefly touch upon some of the defenses and mitigation approaches. So let's get started. So I'm sure you must have definitely seen this particular chart in some shape or form yesterday. But for the sake of setting the context, let me briefly go over it once again. So I think of federated learning as a paradigm for crowdsourced model training, right? And in this, multiple parties, they collaborate and engage in a multi-round protocol for training a model. In each round of model training, the agents train a local model update using their data and share these model updates with an aggregator node. The aggregator node can pick one of several possible fusion algorithms, aggregate these model updates together and create a model for the next round. And this goes on for a set of rounds before the model converges. Now, the idea here is that while all of this is being done, the raw data never leaves the trust domain of any of the agents. Right? So the question is, why is federated learning useful? Now, first up is regulation. Now, with increased awareness of towards data privacy, many countries have either already enacted or they are in the process of enacting stringent privacy laws. And non-compliance with these laws might result in hefty financial fines or liabilities, right? Or other liabilities. And so federated learning can really help you in that. So it allows you to comply with some of these privacy regulations. In similar vein, trade secrets and other proprietary data is never shared. And while you can still benefit from the richness of the data, so federated learning really helps you there as well. Recent results have shown that when you are training model using federated learning compared to centralized learning, you have a smaller carbon footprint. Admittedly, these are early results, and these are also subject to energy policies in different countries. But nonetheless, these are positive results. And finally, the sheer pragmatics, right? You have a much larger computing power today in edge devices than it was before. And also network connectivity is getting better. So with the advent of 5G, you now have much larger bandwidths and lower latencies. So together, the confluence of these factors really enables you to kind of deploy federated learning at scale. Now, federated learning, one of its key benefits is that it brings computation to the edge. It truly, allows us to do on-device training. Now, there are several domains which stands to benefit from this, and one of them is IoT or cyber physical systems in general. Now, these devices generate data which are typically sensitive to the end user. So federated learning allows you to exploit the richness and the diversity of the distributed data while simultaneously preserving the privacy of the end user. Another domain which has really benefited from federated learning is healthcare. For example, Mount Sinai recently published one of its studies saying that they have used federated learning in training one of their models for predicting how COVID-19 patients will progress, how the recovery of COVID-19 patients will progress. Mobile applications, we know that Gboard already deploys federated learning for improved work prediction. Similarly, in the enterprise setting too, federated learning has unlocked a number of use cases. Now, if you think of an acquisition or a subsidiary-based model, you might have offices in different geographical regions, which are again governed by different compliance or regulatory rules. And what federated learning allows you to do is comply with these rules while still operating as one single virtual organization. We have encountered use cases where banks wanted to collaborate to create models for identifying money laundering or financial or fraudulent transactions. And those are also made possible through federated learning, when banks do not actually have to reveal any information about their customers, but they could still bring in, collaboratively collect their insights together to train this model. So a lot of very interesting use cases have been unlocked through federated learning. Now, with its increased adoption in some of these very critical domains, I think it becomes quintessential to get an estimate of the threat perception when we kind of go ahead and deploy these systems. So let's consider crowdsourced systems in general. So, it has three broad operational components. The platform, which can be used for collecting data, and which also runs the protocol. Basically, execution of the protocol happens on the platform. You have the data, which is either provided by the end user, or these are sensory outputs. And finally, the algorithm of the protocol, right? So these are basically, it could be the communication protocol or some learning algorithm and so on and so forth. So in the past, each of these components have been attacked, right? So the integrity of platforms have been compromised through various malwares. For example, the Mirai botnet attacked IoT devices, and this was used to kind of mount large-scale distributed denial of service attacks. More recently, SolarWinds is another example where the platform was compromised, and the attacker was able to kind of mount remote surveillance on sensitive assets. And as recently as last month, in the state of Florida, the water system, All Smart Towns water system was briefly hacked, and the attacker ended up increasing the concentration of certain chemicals in the water. So, and the source of most of these attacks have been traced to very weak credentials or default credentials that were used by the administrators. When it comes to data, one of the things that I wanted to kind of highlight here, and which is often ignored when we think of federated learning, is the influence of social media or social networks, right? So one prime example being Microsoft's chatbot Tay, and this was taken away one day after it was deployed. And the reason being, Twitter users kind of grouped together and started teaching Tay racist and anti-Semitic rants, right? More recently, GameStop. The way I would like to think of GameStop is you have a model which is being used for predicting your stock prices, and the model is reliant on distributed data, which is basically selling and buying prices from different users. And what GameStop showed us is that a bunch of motivated users could manipulate the input to these models and cause it to behave in a certain way. Or, again, no one is challenging whether it was legal or not. But again, this is, users have the power to influence the prediction of these models. Finally, when it comes to algorithms and protocols, the data that is being shared by these algorithms or that is required, the way data needs to be shared as part of these protocols can lead to various kinds of privacy threats. And again, if the platform is compromised, we have also seen that the attacker could end up changing or perturbing the flow of the algorithm itself. So the logic could also be perturbed. So these are some of the security exploits that have taken place in the past. Now, in addition, when we consider federated learning in particular, there are additional vectors that could also be exploited. For example, the interaction duration. When we think of crowdsourced systems, then typically the interaction is one time with the data provider providing the data to the aggregator node, and then the interaction typically ends. But here in federated learning, there is a continued interaction with a possibly untrusted provider during the entire course of model training. And this provides the attacker the ability to calibrate the attack and maximize the impact. The other vector here is the opacity of the shared data. Now, this was done to protect the privacy of the participant or the agent who was in federated learning. But an attacker could actually use it to his or her own benefit, right? So when the data is, for example, when model updates are shared with the aggregator, there is no way to kind of associate a semantic label to what is being shared. And that kind of hinders the ability to use certain anomaly detection techniques, which can benefit the attacker. And finally, the scale of federation, right? Like whether it's between 2 and 100 agents, which is typically referred to as the cross silo settings, or millions of agents, which is the cross-device setting. So based on which of these regimes, the scale of federation lies in, the adversarial strategy can change. And that could also be something that an attacker could use to mount an attack on these systems. Now, one of the questions that often arises is, does diversity really lead to a natural resilience against some of these attacks? Now, diversity can occur manifest itself in multiple ways. One is data heterogeneity between the participating agents. And there is also data redundancy. That is, you can have multiple different agents providing samples for the same class. Then again, the multiplicity of agents. You might have a lot of benign agents who are there, and that helps. Heterogeneity of the backdoors of the attacks that you are going to mount, and also multitask learning. They all provide some sort of resilience again. Finally, the generalization of the model and the resilience of the training algorithm. It is resilient to noise in the training data. So these are all factors that contribute to the diversity, and to some extent, it introduces certain resilience in the system. But more recent work has shown that while the above factors can make attack difficult, they don't seem to be enough to stop a motivated attacker from mounting attacks. So then let's get back to the threat analysis. Now, as you have seen in the past, there could be several different ways in which the system could be attacked. So there could be privacy threats, evasion attacks, and model poisoning. Now, in the interest of time in this talk, I'm only going to focus on model poisoning attacks and see how these attacks can be evaluated in both cross-silo and cross-device settings. So for those who are already familiar with model poisoning attack, this is going to be a very quick recap. For others, it's a very brief introduction into how model poisoning works. So if you think of federated learning, you never share raw data with the aggregator node. So the only way to introduce poisoning is to use your model model updates, right? So that's how it gets the name model poisoning. So you are introducing backdoors into your global model using your model updates as a poison model updates. Now, model poisoning could be done by a single malicious agent or again by a group of colluding agents. Now, what makes this attack very difficult to detect is that an adversary could introduce very targeted set of backdoors. And by backdoors here, I mean specific set of samples that an adversary wants to get misclassified. So these backdoors could be introduced while simultaneously preserving the model performance on all samples which are not part of these backdoors, right? So basically, it becomes really hard to identify that the targeted model is already poisoned. And typically, an attacker's objective, as I mentioned before, is to minimize a combination of both the benign loss as well as the adversarial loss in the backdoors. Now, we in our own work, we try to check the feasibility of model poisoning. We did that in a typical cross silo setting that is around 10 to 100 agents and 1 to 5 malicious agents. So what we observed is that a simple targeted model poisoning attack where the attacker just optimizes for the adversarial loss is enough to get a successful attack. So the red line on this plot here shows that you can actually mount very successful attacks just by updating, optimizing the adversarial loss in the attacker. But we also wanted to maintain stealth. So we went ahead and looked at the distribution of the model updates that are provided by benign agent and a malicious attacker, right? And we observed that this signature differs a lot. And this kind of could be used by an aggregator node to kind of identify that some sort of attack is going on. So what we did was we modified our optimization scheme to now jointly optimize for both the benign and the malicious objective. Why? And also introduce stealth constraint to minimize the difference in this distribution of the weights. One of the reasons why we took to joint optimization was because we observed that the validation accuracy on the malicious update was much lower than the validation accuracy on the benign update. Now, when we changed our optimization strategy, we found that the validation accuracy of the malicious update improved, and the distributions also got a lot more closer. We finally ended up with a strategy of alternating minimization, where we alternately optimize for the benign and adversarial objectives together with the stealth constraint. Now, this allowed us to not only maintain a fairly successful attack, but also increase the validation accuracy of the malicious update. And also the weight distributions were now very similar, and this did not act as a discriminatory signature for identifying these poisoning attacks. Several variations of poisoning attacks have also been proposed. One of them is the distributed trigger attack, wherein the global trigger itself is divided into multiple local triggers, which are then passed on to different colluding attackers who kind of use their model updates to inject these trigger into the global model. Semantic backdoors have also been talked about, wherein instead of a single sample, you kind of use a group of samples which have a similar semantic property, and all of these are introduced as backdoors in a global model. We also evaluated model poisoning attacks at scale, and when I mean scale, I mean cross device settings, that is relatively large number of users, 35,000. Now, what we observed is that in these settings, just the attack success is not a good measure. So we defined a new metric, we call it the outsized impact factor, and it is defined as a fraction of successfully inserted backdoors divided by the fraction of malicious agents. So it helps measure the success of an attack relative to the fraction of compromised agents. Now, an OIF of 1 indicates that at least the number of backdoors or the fraction of backdoors that have been inserted is equal to the fraction of malicious agents. Right? We observed two things. First is the model poisoning attack tends to have an oversized impact. So compared to prior work in a very similar setting with fewer number of attackers and the same attacker frequency, instead of 300 backdoors, we were able to inject 3,000 backdoors. And the effect of collusion is that now attackers can reduce the amount of boosting and hence circumvent some of these norm clipping defenses that have been proposed. So these are some of the observation that we made when we evaluated model poisoning attacks at scale. Now, this is also midway into my presentation, where I'd like to switch gears a little and talk briefly about some of these defense or mitigation approaches that have been proposed. So again, I feel that there are a holistic approach that is needed to securing federated learning deployments. That is, we need to secure the platforms. We need secure aggregation schemes to protect against privacy attacks. We also need resilient fusion algorithms for model poisoning attacks and resilient model training to handle evasion attacks. Again, admittedly, evasion attacks are not really specific to federated learning, but nevertheless, they are mounted on models that have been trained using federated learning. So you would want to have policies or mechanisms in your federated training itself, which would equip these models to handle evasion attacks. So in the next few charts, I'm going to talk about resilient fusion algorithms for handling model poisoning and evasion attacks. Now, while experimenting, some of the things that we found was that model poisoning attacks typically operate in the final few epochs, and they modify parameters corresponding to the feature extractor layers. And this observation is also validated by other research in other research papers. Finally, boosting of malicious updates is required for injecting or inserting a backdoor. Now, this naturally leads to a heuristic defense of layer freezing, wherein you can freeze all layers of the network except the classifier layer. Now, this in isolation again does not work, because an adversary can add a lot of noise to the classifier layer and still go ahead and insert these backdoors. So we introduce norm clipping together with layer freezing, and what this does is it bounds the it limits the influence that an attacker can have, and leads to a good defense against model poisoning attack. But this is still a heuristic defense. To move to provable robustness, we changed layer freezing to top K sparsification. That is, we only use the top K gradients to update our model, and all the remaining values are set to 0. The intuition here is that an attacker's objective will typically be opposed to that of the benign agents, and hence they will disagree on the coordinates to update. Now, this with norm clipping we show that we can provably bound the attacker influence on the global model. Now, we tried this defense on model poisoning attacks at scale, and we are able to really bring down the OIF. Like, this is a quick example on CIFAR 10. 50,000 samples, number of agents over which we simulated was 10,000, number of attackers is 100, and backdoor size that we provided to the attackers was 500. So we wanted the attackers to inject 500 samples. Now, for an OIF of 1, the number of backdoors inserted should be around 500, but what we see is for the point on the rightmost point, the OIF is approximately equal to 0.01, which means that the number of inserted backdoors is roughly equal to 5. So really the defense reduces the attacker's ability to insert these backdoors. I'm going to very quickly talk about some of the things that we have been investigating for handling evasion attacks. Now, recap of evasion attacks. These are basically adversarial examples which are created to elicit targeted misclassification by the models. And these are mounted at inference time. Now, one way to harden models against such attacks is to expose it to adversarial examples during training itself. And one particular strategy is adversarial training. It uses a minimax formulation, wherein the inner loop is a maximization of the adversarial loss. And the idea here is to find adversarial counterparts for every sample in the training set. The outer loop optimizes the model parameters theta to minimize the expected loss. So our idea was simple. We wanted to kind of adopt adversarial training to federated settings. So we used federated averaging, which is one of the most popular fusion algorithms, as our fusion algorithm, and just allowed the agents to train models using adversarial training. So as a sanity check, we just wanted to verify that does fusing these individual models lead to any improvement in either the clean or the adversarial accuracy. And to our surprise, we found that when we fused models which have been trained using adversarial training, indeed, it leads to better adversarial accuracy and natural accuracy. Now, we also observed certain issues. Two of them were that there was a significant drop in both the clean and adversarial accuracies when using non-IID data for federated learning. And also, there was an increase in convergence time. So approximately 800 epochs to reach convergence for the model. We attributed this to large-scale model divergence. That is, the representational similarity of the layers at the different agents was very low when they were being trained using adversarial training. And we can intuitively understand that, right? The models are getting tuned to their own set of adversarial examples, and hence they start to diverge. And when you take these divergent models and fuse them, the gains of fusion kind of tends to reduce by a lot. We also observed that the frequency of synchronization with the aggregator affects the speed of convergence and performance. And this is, again, this is also intuitive. That is, the more number of local adversarial trainings you do, the models tends to diverge more. And then, it kind of affects your both your model convergence and performance. So towards that end, we propose something called federated dynamic adversarial training, wherein the key idea here is to regularize the training loss. to minimize catastrophic forgetting. So we kind of prevent, while doing adversarial training, we force the model to not forget everything that it saw during the previous round of fusion. And we also created a synchronization schedule. That is, we start by with a delayed, with a very large number of local epochs of adversarial training, and as training progresses, we reduce this number and synchronize more often. What we observe is that it really speeds up convergence. So what took 800 epochs can now be achieved in 50. And we also observed that the models at the different agents showed much common representational similarity. Much higher representational similarity. And I forgot to mention that we measure similarity using the SVCCA scores. So higher value indicates greater similarity. So I think I have 5 more minutes of time left. So what I wanted to do was briefly touch down upon a slightly different area here. And again, this is basically to introduce an open problem. So the proposed approaches that we have been studying, or that have been proposed, proposed by others, are effective in defending against threat. But federated learning is pretty much a black box. So the question is, can better understanding of the process help with robustness? And towards this end, the field of interpretability could be of use, right? It provides tools to explain machine learning models and their decisions. So an obvious question is, can explanation help with federated learning and its robustness? So we did a quick experiment here. We used several interpretability techniques to identify what are the important features in a particular, that are used by a particular model, which is trained by benign agents alone. So we trained the federated learning models using only benign data, and we try to understand what are the important features that this model looks for in a given data sample. And we did the same for a malicious or poisoned model. And we wanted to identify if the important features that are used by these two models are different. Now, what we observed is that the current interpretability techniques are not sensitive enough to identify these differences very accurately, but still we can identify some differences in the saliency map. Again, the utility of an explanation really depends on the role of the end user, whether it's a developer, researcher, or consumer which is asking for this explanation. Now, when you think of federated learning, our goal is not only to explain a model decision, but to really understand the effect of the training samples on the model behavior. Now, explanation by example is one technique that has often been considered helpful in explaining the role of training data towards the model decision. But again, revealing any information about the training data directly conflicts with the premise of privacy for which federated learning was designed. So I see that there is a nice trade-off or a conflict that arises here. And at this intersection, there are several open research questions that probably are interesting and needs to be answered. So I'd like to wrap up by briefly advertising the work that's happening within IBM on federated learning. So we are heavily invested in both developing and adopting federated learning. So we recently released community edition of our IBM federated learning framework. It has various target users. For example, data analysts can automatically enable federated learning for their models using the well-known frameworks, and they need not know about the intricacies of federated learning. Enterprise application owners can deploy federated learning in production environments. And finally, researchers can use the platform to kind of compare it with existing techniques and also extend it with their own. What currently exists, we have support for a large number of models. So you can federate these models. The library is almost agnostic to the runtime library that you have used. It could be Keras, it could be TensorFlow, or it could be PyTorch. It supports several standard fusion algorithms and some advanced ones as well. There are privacy primitives that you can directly, that are integrated with the platform, and you can kind of use this differential. There is a differential privacy library that you could use. And furthermore, IBM also has support for the adversarial robustness toolbox, which is basically an implementation of state-of-the-art attacks and defenses. And also the AI explainability 360, which has a number of state-of-the-art explanation mechanisms. So in summary, I think securing federated learning requires addressing concerns at all levels of the stack. And I believe the community should strive for deeper understanding of realistic threats, right, which happens during deployments. And these are not only for image-based classification tasks, but should also be for NLP, reinforcement learning, and so on. I think emerging ideas around model interpretability could be very useful in understanding model training in distributed setting. And finally, I think IBM platform, together with some of the other resources, provides a very rich ecosystem, which allows researchers to experiment with various facets of the problem that I discussed. Thank you very much. I'm ready to take questions now.
Thank you very much, Supio. This is a very informative talk. So yeah, we have some Q&A for you. Yeah, so one question is from Abhishek. Is there any relationship here between the number of clients that you're using in federated learning versus the difficulty for the adversary in successfully poisoning the models?
Definitely. I mean, for poisoning models, you need to have boosting. And the need for boosting is because the benign updates can tend to overwhelm the update from a malicious agent. And so this was also our intuition behind some of the experiments that we ran on large, at large scale, thinking that when the number of benign agents are really large, then the influence of a model poisoning attack would be limited. But contrary to that, we found that a very small number of attackers could still go ahead and have an outsized impact, considering the number of backdoors that they can insert. So clearly, there is an influence of the number of benign agents that are present, but the impact of a small number of malicious agents is oversized, and that's probably what is the main conclusion that we had from our experimental setup. Does that help?
Yeah, it does. The one who asked is happy. So, okay. So yeah, one more thing is I just noticed the IBM Federated Learning Library that you showed a slide on. So when we search for it, we do see a GitHub link for it. So is it completely open source or is it partially open source?
I think the community edition is open source, so you can access all the code in the GitHub, and yes, you can it's open source.
Ah, very nice. Yeah, we'll check it out. So we have one more question on the Slack from Hrishikesh Kamath. The question is, can warm-up training use methods such as MPC to reduce the accuracy drop in federated learning when you have non-IID data distributions?
Very interesting. I guess that's possible. We haven't tried it, but I think it's quite possible. I think and I think this can also be related to the fact that when you have a low synchronization frequency, you still see a higher convergence with non-IID data. And I think this goes back to the question that was posed, that when you initially train for larger number of local epochs, you kind of stabilize the model before you go ahead and start fusing. And I think warm-up training would really help. It is, again, something which will benefit this. So I kind of feel that intuitively it should help with when you are training federated learning with non-IID data. But again, I have not tried it. But I think this is definitely a good idea.
Cool. Yeah. And then one more question. I think it's just coming as we talk. So the next one is, do you see, this is kind of open-ended, do you see differential privacy or other formal privacy in general going hand in hand with adversarial robustness work for federated learning?
Absolutely. So I think there was a paper by Sun et al. I think Peter Kairos is also a co-author on the paper, wherein they actually looked at adding noise during fusion as a mechanism of introducing robustness to some of these poisoning attacks. So a later work showed that, and again, it was not really differential privacy. They were just adding Gaussian noise. So they didn't want to kind of, they were not kind of providing any differential privacy guarantees per se. But I think, but later work was kind of able to show that, you can mount attacks which circumvent this noise addition-based defense. But I think a user-level differential privacy has also been proposed and has been shown to be effective in training large-scale federated learning models. I think training large-scale recurrent language models is a paper by McMahon et al., which shows that user-level differential privacy really helps with with some of these attacks.
Very interesting. Yeah, this is very cool. Yeah, so they're thanking you for the answer. So very cool. Thank you, Supriyo. This is a really interesting and very informative talk.
Thanks, Praneeth. Thanks everyone for the questions.
Yeah, thank you. Okay, I will share screen and we will move with the rest of the session now. All right, so that was a really nice talk by Supriyo from IBM. So let's move ahead with our research talk part of the sessions. So we have our first research talk for the morning session on label leakage and protection in two-party split learning. So this is certainly a very interesting topic that came up in quite a few discussions yesterday as well. So this is by Oscar Lee, Jiankai Sun, we have Hongyi Jin, Junyuan Chong from Carnegie Mellon, ByteDance Inc. and University of Washington.
In this video, we'll present our work, Label Leakage and Protection in Two-Party Split Learning, that was completed at ByteDance. Prior work has shown that raw data can be leaked through communicated gradients in horizontal federated learning. In our work, we show that data leakage can also happen in vertical federated learning, where data is partitioned according to features instead of different devices. Specifically, we first identified that in a realistic two-party split learning problem setting, one party can uncover the other party's private label information using the communicated gradients. To protect the participating party's private label data, we then propose a theoretically justified random gradient perturbation method that strategically calculates how much noise should be applied. To motivate our problem setup, we first discuss a real-world setting for split learning. Here, we have two parties where the first party is an online media platform and the second party is an e-commerce company that displays advertisements on the media platform. A user on the platform will periodically be shown advertisements from the e-commerce company. If the user clicks on the ad, he or she will then be directed to the product page of the e-commerce website, over which he or she can then decide whether to make a purchase. For this same user, the two parties have different features. The media platform has the features of the user's interest and viewing history, while the advertiser has the binary label of whether a purchase is made or not. In many real-world scenarios, the advertiser is unwilling to share its users' purchase information with the media platform due to privacy and business secret considerations. As a result, for both parties to jointly learn a model that predicts users' purchase behavior, we can formulate this as a two-party split learning problem. The main question that we study in this work is whether the label information can still be leaked in the split learning setting where no raw data is communicated. To abstract the previous example, we consider the two-party split learning problem, where the passive party on the left and the active party on the right want to jointly learn a model for a binary classification problem. For every training example pair x, y, the input feature x is stored on the passive party side, while the binary label y is stored on the active party side. Here, the model is represented as a function composition h of f. The passive party wants to learn a representation function f that maps an example's feature x to a vector representation in Rd, while the active party wants to learn a prediction function h that takes the representation computed by the passive party and return the positive class logit lowercase l. Here, the representation f of x is communicated from the passive party to the active party before h is applied. With the logit l, the predicted probability of the positive class tilde_p1 is calculated through the sigmoid function, and the entire model h of f incurs a cross-entropy loss of capital L with the correct label y. To train the entire model h of f using gradient descent, the active party starts the gradient computation from the cross-entropy loss and compute the gradient with respect to the logit. The scalar derivative is equal to the difference between the predicted probability of the positive class and the actual label. Then, using chain rule, the active party can propagate the gradient to h's parameter. In order to also update function f's parameters on the passive party side, The active party also needs to compute a gradient of the loss L with respect to the representation vector f of x. We denote this representation's gradient by g. The active party needs to communicate this gradient g back to the passive party. After receiving g from the active party, the passive party can then keep backpropagating and update f's parameters. If we look at the form of the communicated gradient g, we'll see that by chain rule, it is a function of the active party's label y. Thus, a natural question to ask is if this communicated gradient will leak the active party's private label. To answer this question, we give a simple way that can uncover the label y for many practical two-party split learning applications. Here, we look at the 2 norm of the communicated gradient g. For many real-world datasets in online advertising or healthcare applications, at different iterations throughout training, the absolute value of p1 minus y is consistently larger for the positive examples than the negative examples, as shown in the figure on the left. This is specifically due to the fact that the learned model is in general less confident about a positive example being positive than the negative example being negative. On the other hand, as we see in the middle figure here, for both the positive and negative examples, the 2 norm of the gradient vector of h is roughly of the same magnitude. As a result, the communicated gradient g's 2 norm, which is the product of these 2 terms, is generally higher for the positive examples than the negative examples, as shown in the right figure. Thus, by looking at g's 2 norm, the passive party can very accurately figure out the corresponding example's hidden label stored on the active party side. More concretely, using g's 2 norm to predict the label y has an AUC of higher than 0.9 throughout training. This shows that the active party's labels are significantly compromised. Because of this possibility of label leakage through gradient computation, the active party should aim to send the essential information of the gradient without actually communicating its true value directly. In our work, we achieved it through random perturbation. Before sending the gradient g, the active party will now randomly perturb it and send the perturbed gradient g tilde to the passive party. Here, by linearity of expectation, as long as the random perturbation is unbiased, the computed gradient for f's parameter will also be unbiased. Thus, we naturally consider adding zero mean Gaussian noise as perturbation. Because the positive and negative examples have very different gradient distribution, as seen from the 2 norm analysis, we consider using Gaussian noise with different covariance matrices sigma 1 and sigma 0 to be added to the positive and negative examples gradients respectively. We denote the gradient distribution of the positive and negative class by p tilde 1 and p tilde 0. Additionally, for the training loss to be optimized efficiently, we also want the random perturbations variance to be as low as possible while achieving the same level of protection. Thus here, we need a formal notion of label protection quality. Here we consider a general class of labeling functions where each function I sub a is the indicator function of the corresponding set A. We think of each of these functions as a classification rule that guesses an example's label to be 1 whenever the example's communicated gradient g is in the set A. This general class of labeling functions would contain the 2 norm method that we identified previously when we let the set A to be the set of vectors with 2 norm greater than some threshold t. With this class of functions defined, our goal is to perturb the gradient so that none of these functions is able to guess the unseen label accurately enough. For specific labeling function I sub a, we measure its performance in guessing the label by the detection error, which we define to be the average of the false negative rate and the false positive rate. Here, the false negative rate refers to how frequently the labeling function would wrongly think that the perturbed positive gradient g comes from a negative example, and the false positive rate is exactly the opposite. To protect against this entire class of labeling functions, we focus on the function that guesses the labels most correctly among this class, which by our definition is the function that has the lowest detection error. This lowest detection error is exactly equal to a value involving the total variation distance between the perturb positive and negative gradient distributions. This is specifically by the definition of total variation distance. To guard against this worst-case labeling function, the active party would want to maximize this worst-case detection error. To do so is equivalent to choosing the noise variable's covariance matrix so that the total variation distance between the perturbed gradient distributions is minimized. However, directly solving this unconstrained problem will result in adding infinite amount of noise to the communicated gradient. Thus, to allow the training optimization to proceed successfully, we add a power constraint. The constraint upper bound capital P controls the amount of added variance and is a tunable hyperparameter to trade off between protection quality and learning performance. Because the total variation distance between high-dimensional distributions are analytically intractable, we instead minimize the symmetrized KL divergence upper bound of the TV distance. With some additional constraints and assumptions, we can solve this optimization exactly very efficiently. After getting the optimal covariance matrices, the active party can then sample from the corresponding Gaussian distribution and add it to the gradient G before communication. Experimentally, we find that our approach can successfully defend the two-norm label uncovering methods described before by achieving a much lower leak AUC of around 0.5 instead of 0.9. Additionally, by varying the constraint constant P, our approach can flexibly trade off between the amount of privacy protection and the learned model's test performance. We also show that due to the strategic perturbation, our approach can achieve better privacy versus performance trade-off than other naive protection baselines, such as adding isotropic Gaussian noise. Please check our paper on arXiv if you're interested, and contact us if you have any questions. Thanks.
Thank you very much, Oscar. This is a really interesting talk. So let's see if there's any Q&A. Looks like Oscar is available on the Zoom call. Yeah, one question I had was so what is the effect of the sample size in being able to distinguish, even if you're making sure the Jensen-Shannon divergence is reduced? Is there an effect on the sample size where the attacking party can collect more and more of the gradients? And then I believe it's like a hypothesis testing problem. So
yes,
is there a relationship between the TV divergence and the sample size that is more recent?
I think, well, in some sense, the sample size is indeed like a real problem. But as you keep on, for every single iteration, when you do the training, when you receive the gradients, well, the passive party side will actually update the model. Well, technically, when you update the model, the distribution would change automatically, even without like doing any perturbation. But then, because like the fact that the update is like probably very small in terms of like changing the actual gradient distribution, so it is possible that like across multiple epochs or like even just neighboring iterations, it is possible that the distributions would actually be very similar enough so that if you actually accumulate enough information, you could still uncover like some the relationship between like the two distributions. But in this work, we haven't exactly considered this case. We focus on like at any snapshot in time, we want to like protect exactly, make it like impossible to like distinguish between the positive gradients distribution and negative gradients distribution, if that makes sense.
Got it. Yeah. I guess maybe if we could sample the covariances, it means in a different way from round to round, where they're kind of diverse from the previous round. So this is an interesting question. Yeah, but that makes sense. Very cool. So we move on with the.
In this video,
we move on with the next part of the talk. So the next talk we have is on communication efficient multimodal split learning for mmWave received power prediction. So we have two talks from this group on this problem, but from a different aspect. So this is from Yusuke Koda, Jihong Park, Mehdi Benes, Koji Yamamoto, Takayuki Nishi, and Masahiro Morikura from Kyoto University, Beacon, and the University of Oulu.
Alright, welcome to this video. I'm Yusuke Koda in Kyoto University. The first video, I'd like to talk about the application of split learning to millimeter wave wireless communications and seek for communication efficiency and privacy. This is a joint work of Professor Mehdi Benis and Jifong Park and professors in Kyoto universities here. Okay, in the first video, I'd like you to take away two things. First, it is why it is important to utilize split learning and multimodalities in wireless problems. And we consider millimeter wave residual power prediction. And multimodality means array image modalities and RF modalities in this video. Okay, and the second, I would like to mention the optimization of multimodal split learning. This is motivated by communication costs and privacy. Alright, let's get into the first topic and let's find out why this multimodal split learning is important to residual power prediction. Okay, this is a background, and in case you are not familiar with millimeter wave communication, I'd like to state the problem of millimeter wave communications, and that is sudden variation on RF signals caused by moving obstacles. Here's what I mean. Let's say base station communicates to user equipment via millimeter waves, and pedestrian blocks this line of sight path. In this case, the UE user equipment experiences a sudden decrease of residual power value, and this is a blockage event. Okay, and the problem is that if you look at only RF received power signals, you cannot expect this blockage event, right? So the UE may take some reactive actions against this blockage event, right? So the problem is how to this blockage event in advance of the occurrence of the blockage event. That's why we would like to use camera images, because this camera image captures the pedestrians regardless of the occurrence of blockage events, right? So this is a system model, and the camera image is sent by the, say, surveillance cameras and fed into convolutional neural networks and recurrent neural networks and output future residual powers. And the prediction result is here. This is a 100 millisecond look ahead predictions, and this gray line represents the ground truth, and this red line represents the RF based predictions, and that does not match to the ground truth, right? But if you utilize image, you can perform more accurate predictions. However, there's two key problems we would like to focus on in this video, that is privacy and unimodal predictions. And the first one is privacy, because the surveillance camera may involve some privacy sensitive information such as humans' trajectories, right? And in case of this surveillance cameras, images are not available due to privacy concerns, you cannot predict future residual power value, right? So we would like to devise some privacy preserving future residual power prediction systems. Okay, and the second is prediction result relies on only on image, and that is unimodal predictions. Although I mentioned that the RF residual power is not informative to predict some rapid variation, RF residual power is informative in case of this RF signals is correlated with in the long term scenarios that is low line of sight path and line of sight path conditions. Alright, this motivates us to utilize multimodal split learning, and the proposed scheme is here. And the first thing is that this is privacy preserving, right? Because camera images, you don't have to upload raw camera images, but instead you can upload forward propagation signals, that is CNN feature activations. Okay, and the second thing is that you can perform multimodal prediction, because this upper recurrent neural network layer can combine the feature activations related to camera images and receive the signals. Okay, that's what proposed scheme looks like, and this is compared to unimodal prediction in the next slide. Here, this is a performance comparison in terms of future ratio power prediction results, and the gray line represents ground truth, and the red line represents RF signals-based prediction, and blue line represents image, and yellow line represents image plus RF, the proposal scheme. Okay, and you can find out two things. First, image plus RF well match to the ground truth in the rapid variation ratio powers with the help of image modality. And second, I would like you to focus on this line of sight path conditions, and you can find that image plus RF matches to the ground truth better than the single unimodal predictions. Okay, this is because the RF signals in the image plus RF, and this validates the effectiveness of multimodal predictions, that is image plus RF modalities. Alright, in the second topic, I would like to explain the communication efficiency and privacy in multimodal split learning. Our key idea to solve this problem is that varying the pooling region size contributes to both communication cost and privacy. Here's what I mean. This is an overview of our multimodal split learning, and it has CNN, and it has average pooling here, and this is a pooling region size. And the first point is that as this pooling region size becomes higher here, and sorry, this is 10 by 10, the pixel size becomes smaller. So that means the output size to be uploaded is smaller. So that contributes to the communication cost, right? And the second thing is that as pooling region size becomes higher, it is harder to find out where pedestrian is, right? So this actually contributes to the privacy. Here, this is a result of communication costs and test accuracy in terms of RMSE according to the pooling region size. This RMSE is better. The smaller the better. Okay, and you can find out two things. First, the pooling region size of 4x4 reaches the best accuracy. Okay, and this indicates that you can reduce these communication costs for free in terms of RMSE, that is, without sacrificing the test accuracy. This is an important thing. And the second thing is that you can enhance the communication costs by enlarging the pooling region size. Right, so this indicates that you should carefully determine this pooling region size with consulting to the test accuracy in RMSE. Alright, this is the results of privacy. This measured by image similarity level between the raw image and CNN output image. And the x-axis represents the communication cost. And you can find out that as pooling region size becomes higher, image similarity level becomes smaller, which indicates higher privacy. So okay, let's take a look at a toy example of how to optimize the multimodal split learning. This is our MSE result, and the right graph shows the privacy level. And the toy question is, what's the optimal pooling region size with the objective of minimizing the accuracy, RMSE subject to similarity level is smaller than 0.34 and communication cost is smaller than the 5,000. And the solution is this 10 by 10 is optimal. Okay, and this is a toy example, but this the key takeaways is that this changing pooling region size gives an opportunity to optimize multimodal split learning in terms of test performance, communication cost, and privacy level. Okay, that's all for the first video, and I would like to move to the second topic, that is multiple cameras in multimodal split learning.
Thank you very much, Yusuke Koda. I think he is on the MIT Zoom, so he's available right now for questions. So let me check the Slack. Yeah, so there will be questions posted in Slack now and after the second talk as well. So you can also join there, and the speaker is going to answer the questions over Slack too. So one question I had was more generic. So what is the, what are the applications that you see to having these two different signal collection platforms? Are you thinking of drones, or what are the applications that you see for this kind of work?
Hi, hello, I'm Yusuke.
Hey.
I'm Yusuke here, and the application, the first application is like 5G communications, like generic drones, static base stations. Yeah, everything is fine, and a key point is that yeah, 5G requires larger bandwidth, so the higher capacity. So this is an application of millimeter wave communication, and we target at this 5G, 6G communications. Okay.
Very cool. Yeah. So there's more questions from Krishnan Raghavan from Argonne National Lab. Yeah. Do you go through some kind of a search process to get this optimal value that you're looking for when you optimize?
Okay, do you go through some kind of a search process to get this optimal? In this experiment, we performed some empirical, rely on empirical results. We surveyed the RMSE and privacy level and communication costs, and you create some tables and search for like exhaustive search. Yeah, that's my answer.
Very cool. Yeah. One other question is, your paper mentions the manifold mix-up technique. What part of the pipeline is this helping with? Like, what is the problem that it is solving here in your case?
All right. It's a second topic, right?
Okay. So I guess we move to the next video now, maybe, and then.
Yeah.
Okay.
Yeah. Please go ahead.
Cool.
All right.
Okay, so we have the same group presenting distributed heteromodal split learning for vision-aided wave received power prediction.
Hello, this is Yusuke Koda in Kyoto University. And in the second video, I would like to extend multimodal split learning for multiple camera case. This is also joint work from Lebanese professors and Jihon Park and professors in Kyoto University. Okay, here's an outline, and we would like to mention two key takeaways. We consider multiple camera cases in this video, and we answer the following two key questions specific to the multiple camera cases. And first question is how we can make a different frame rate in distributed cameras compatible to each other in a communication and energy efficient way. And the answer is that we would like to propose a manifold mix-up interpolation, that is interpolating features in upper layers. Okay, and the second question is how we can design a split learning scalable to the increase in the distributed cameras. In the split learning, upper layers input size increases as distributed camera increases. If you would like to combine images from distributed cameras, and we would like to provide the answer of manifold mix-up aggregation. This is an average-based aggregation. Can be realized scalable split learning in terms of the energy efficiency. Here's an architecture of multimodal split learning in two camera cases. We consider two cameras that has a different field of view. Okay, and in this architecture, the key point is this feature aggregation method that aggregates two distributed camera image features. And the reason is that this different field of views images are essentially non-IID, right? So that prohibits from aggregating layer parameters as federated learning. So we employ feature aggregation in the upper base station procedures. Okay, and this aggregated feature is combined into receive power features in the fully connected layers and output future received powers. And given the multimodal split learning in the two camera cases, the first topic is to answer how can we make a different frame rate compatible to each other in a communication and energy efficiency manner. Before we take off our proposal, I would like to mention a problem providing two naive baselines, that is thinning and mix-up. In both cases, we consider two camera cases. The one has higher frame rate and the other has lower frame rate. So that in the camera B is basically lacks the images corresponding to the other one here. In thinning, the camera A discards this redundant image and feeds the remaining images into convolution layers and makes the number of images compatible to the other one. In this case, communication and energy efficiency is better because the input size becomes smaller, so this makes the convolution layers, recurrent layers, computation costs smaller, and communication cost is better than the other baseline because of the smaller payload size. But you discard the essential feature images, so the prediction accuracy may be poorer than the other baseline. And the other baseline is a mix-up that interpolates image features, taking, say, linear interpolation. This outperforms the other one because this interpolates features may essentially helps to enhance the prediction accuracy, but communication and energy efficiency becomes poorer than the other baseline because of higher payload size and higher input dimension. Okay, given these two baselines, we propose the base station side manifold mix-up interpolation. The idea is simple. We take interpolation in the base station side. So that is, we interpolate image features in the base station side. This achieves intermediate communication and energy efficiency because as mix-up, we don't gain the raw image in the camera speed side. And hopefully prediction accuracy is better than the thinning and better than the mix-up that is evaluated from the next slide. Here, this is an experimental setting. We deploy two cameras, camera A and camera B, that has different field of view, and we predict ratio power 500 milliseconds ahead. Here, this is the result of accuracy and uplink cumulative communication costs, and you can find out two things. This green line is thinning, and this is a mix-up, and this is a manifold mix-up, our proposal. Okay, and you can find out two things. First, this thinning achieves fastest convergence due to the smallest payload size. But this mix-up and manifold mix-up achieves better prediction accuracy, slightly better prediction accuracy than thinning. And the key point is that comparing these two cases, the manifold mix-up achieves fast convergence due to smaller payload size rather than mix-up cases. So as expected, this manifold mix-up presents an intermediate result in terms of communication cost, but better performs the thinning and comparable to the mix-up case. This is a detailed comparison in terms of RMSE and applicable communication costs and energy costs. And as I said before, in manifold mix-up performs better prediction accuracy compared to thinning and compared to the mix-up. But manifold mix-ups exhibits an intermediate result in terms of applying cost and energy costs, and actually better than the mix-up case. Okay, let's move to the second topic. In this topic, we answer how to design a multimodal split learning scalable to the increase in the number of distributed cameras in terms of energy efficiency. Okay, first I'd like to mention the problem from increasing the number of cameras. In the set experiment, we employed a concatenation in the aggregation feature aggregation method. That is, say, camera A, the image, and camera B is image. And in this case, as number of cameras increases, the full layer size becomes higher, and that means the energy consumption and memory bandwidth becomes higher as well. Okay, this is our proposal of manifold mix-up based feature aggregation in distributed cameras. The idea is simple. In this case, we average image features into one image and feeds to fully connected layers. In this case, the size of image is constant regardless of the number of cameras, and the size of fully connected layer is constant as well. And that contributes to the memories and energy consumption. And that's what our proposal looks like. And we know that this averaging-based feature aggregation is provided in the literature, but we would like to emphasize that this averaging contributes to not only prediction performance, but also the energy consumption and memories in the split learning context. Okay, finally, we would like to make performance comparison in terms of RMSE and size of fully connected layers and energy costs between just concatenating image features and manifold mix-up image feature aggregations. And in the manifold mix-up based interpolations, the RMSE is competitive in both cases, but the energy cost in base station becomes smaller. Okay, so this finding shows that you can enhance the energy cost in base station without sacrificing RMSE by changing the image feature aggregation method from concatenating to manifold mix-up aggregation across cameras. Okay, here's a summary. In this video, I answered the following two questions and provided the answer. The first one is to answer how can we achieve makes this different frame setting compatible to each other in a communication and energy efficient manner, and provided manifold mix-up interpolation. The second is answer how we can design a split learning scalable to the increasing the number of distributed cameras, and provided the manifold mix-up based aggregation, that is image averaging aggregation. And that's all for this video. Thanks for watching.
Yeah, this is very interesting. Some questions we have is the output of the manifold mix-up of a different dimension than the features that it is originally trying to interpolate?
Sorry.
Yeah, is the output of the manifold mix-up of a different dimension? Is it of a lower dimension than the data?
Yeah, in terms of the manifold mix-up in the first topic, the frame rate, compatible frame rate, the data dimension is the same. But in the aggregation part, the data dimension is reduced to the one cameras, whereas the concatenation
Right.
gain linearly to the number of cameras.
Right. Is this reduction in payload the main reason why the energy efficiency is improving in the communication, or is it also because the convergence is better? What are the causes for the improvement in efficiency?
Yeah. In the feature aggregation, the manifold mix-up, the reason why the energy efficiency is increased is that we can reduce the fully connected layers numbers of weights in the fully connected layers, and this reduces the energy, the memory,
Sure. Makes sense.
memory consumption, and blah blah blah. And in terms of the communication efficiency, in the manifold mix-up, different frame rate compatible to each other. The manifold mix-ups can be performed in the base station, not the camera size. So the payload size is increased. So relative to the camera side manifold mix-up.
Got it. Makes sense. Are you also doing a mix-up with? So what I understand is you're also doing a mix-up within the base station, and there's also an option to mix up, aggregate the features across base stations. Correct?
Yeah, correct. Yeah, correct.
Got it. Got it. Very interesting. Yeah, this is a very fascinating talk. Yeah, thank you for the talk. So yeah, we can engage more on the Slack.
Yeah, thanks for having me.
Cool. All right. So
Hello, this is Yusuke.
We're moving to the break. So we have a break, and then we'll resume back as in the schedule on the workshop. So this is going to be okay, this is a 15-minute break. So we're going to resume in 15 minutes at 11:30 a.m. EST, Boston time. All right, welcome back to the Split Learning for Distributed ML workshop. So there's a lot of conversations happening in Q&A, and you can talk to speakers and engage on the Split Learning channel on this Slack website. So we move on with the next research talk. This is a distributed min-max learning scheme for neural networks with applications to high-dimensional classification by Krishnan Raghavan, Shweta Garg, Sarangapani Jagannathan, and V.A. Samarnaike from Missouri S&T and Argonne National Lab.
Hello, everyone. My name is Krishnan Raghavan, and I am going to present on model parallelization in deep neural networks. This paper was written in conjunction with Shweta, who worked with me on a summer project with respect to this paper under the guidance of S. Jagannathan and Samar Naike in Missouri University of Science and Technology. To start with, we're going to consider a standard neural network with D layers. Each layer is represented by FT, which represents the nonlinearity at that layer, and WD, which represents the weight at that layer. Now, I'm considering a supervised learning setup in which there is a learning phase and a testing phase, and the data is given to us as a tuple of X and Y. We will consider a simple cost function, which is an L2 norm cost function, which will basically be given as an error square. Error is defined as target minus output of the neural network. The optimization problem that we intend to solve requires us to minimize the cost function with respect to the weight of the neural network, which is collectively denoted as theta. This optimization problem is consistently solved in the literature with different optimizers such as Adam, EDA grad, EDA delta. The common theme in all of these optimization approaches is the fact that they are based on backpropagation algorithm. And there are many drawbacks to these algorithms. We'll start with drawbacks considering backpropagation. To think about backpropagation, we will define the weight update as a derivative of the cost function with respect to weight at that layer. When you describe the derivative of the cost function with respect to weight at that layer, by chain rule, you will split it across many partial derivatives in which all the partial derivatives highlighted in blue are of the activation function. When the value of activation function, there are two components to a partial derivative, the magnitude of the partial derivative and the direction into the sign of the partial derivative. When the value of the activation function is less than 1, that is between 0 and 1 or negative 1 to 1, you will get a phenomenon in which many small values between 0 and 1 will get multiplied. Number of layer keeps on increasing, this multiplicative value starts pushing 0. Similarly, each partial derivative introduce a different direction of learning, which leads to a non-convex optimization, which is really hard to solve. On the other hand, in spite of challenges with backpropagation, on the other hand, there are many challenges with respect to parallelization as well. Standard approach to parallelization is as follows. You have multiple copies of neural network that needs to be maintained. These copies are then spread across different nodes on the neural network. The data is also split across different nodes, and then each neural network in this node is learned based on different types of data, different parts of the data given to them. This setup leads to recognizing an elephant problem in which each part of the element is recognized by a different neural network, and none of them, when this data is merged together, none of them can really give a full picture of the data, which is the standard issues with such approaches. Now, a core issue which leads to these problems with optimization and deep neural networks is the compositional structure of neural network. By compositional structure, we mean the idea that one layer is given as an input to the next layer in a neural network setup. This compositional structure of neural network, if broken, can be a solution to this problem in which you can allow model parallelization as well as data parallelization without getting into problems due to a non-convex optimization. And that is the main contribution of this work, and that is what I'm going to talk about today. So To talk about our distributed learning methodology, we'll take a simple 3-layer neural network where there are three weight parameters, W3, W2, and W1, and 3 activation function, F3, F2, and F1. To start our methodology is inherently dependent on introducing additional variables which take place of each layer in the neural network, such that the connection between one layer to another layer can be broken, and the connection for the input to every layer is this additional variable instead of the previous layer. To illustrate this, let's start by introducing an additional variable Z3 in the place of the top layer of the neural network, that is the third layer of the neural network. With this introduction of first variable, your y hat, which is the output of the neural network, now becomes dependent on Z3 instead of depending on all the other layers, such that Z3 is constrained to be equivalent to the previous layers. Now, this neural network, this is not a neural network unless Z3 is equivalent to Z3 represents all the data that is going to come from the previous layer. Therefore, Z3 has to be constrained to be equal to all the previous layers of the neural network, which is layer 2 and layer 3, 2, and 1. Similarly, let's introduce another additional variable, which is Z2, such that now the output of output Z3 depends on Z2, and Z2 is constrained to to be equivalent to the first layer and the second layer in the neural network. By introducing these two additional variables, our optimization problem has changed now. The change in the optimization problem is as follows. In standard case, our optimization problem, the cost function was written as y minus y hat. By introducing these additional variables, we have introduced the constraints because of additional variables, which is Z3 and Z2, each of which is constrained to be equal to the previous layers. Now note that these constraints are implicitly present in a standard neural network, and we do not think of them as constraints. We just set Z3 equal to the previous layer of the neural network, and there is that. What we are proposing in this work is that instead of setting Z3 equal to the previous layer, we will update Z3, or rather learn Z3, such that we can mimic the output of the previous layers. To learn Z3 as another variable, instead of just setting these constraints equal, we will define a penalty-based cost function in which J, the y hat, introduces two additional components. Each component is a penalty function that satisfies the constraint on Z3 and Z2 independently. If you do this kind of an introduction of an additional variable for every layer in the neural network, what you obtain is for each layer, your input is Z. Z goes through the activation function F. This activation function then gets multiplied by the weight at that layer, and that is your output. That is your output to the output of that layer. Using that output of that layer, you will constrain the input to the next layer to be equal to the output of the previous layer, and this type of behavior will lead to many additional variables. So by constraint, we mean that each additional variable can be introduced an observer that is required to estimate the output at the previous layer. So the main contribution of the main idea in this work is basically that instead of directly learning the neural network weights, we learn Z variables first, such that Z's can achieve the constraints that have been imposed on it as part of the optimization problem. After Z variables are learned, we update the weight parameters. However, this introduction of Z variables introduce additional parameters, hyperparameters that needs to be tuned, such as the penalty function parameters and sparsity parameters, and as follows, because that will lead to computational improvements. But these are too many parameters to set by hand. So what we will do is we will formulate this as a two-player optimization problem where the cost function is maximized with respect to the penalty parameter and minimized with respect to the parameters of the neural network. When the Z constraints are introduced, this final cost constraint optimization problem is written as follows. With respect to this new optimization problem, theoretically, we can show that this new optimization problem is equivalent to the old optimization problem. We can also show that the saddle point exists, and a main result of our paper is that each of these optimization problems independently is convex, and this can be really easily thought about because each of these optimization problem only depends on the weight at that layer and Z at that layer, and provided the activation function is chosen properly, this optimization problem is convex with respect to the parameters at that layer. Overall, as I mentioned before, the algorithm basically involves two loops. In the first loop, you have to update all the z's such that the z's approach the constraint that they have been imposed on. And then once this loop is finished, the outer loop gets updated. The important point to note is that no communication is happening between each layer of this neural network. Each of these layers can be set up on different nodes in a highly parallel supercomputer, and data and so this, which will provide us with data and model parallelization, which was the aim of our work in overall. In result, when we use Stannard's hyperbolic activation function and vary the number of layers, we see how well the rate of convergence and the accuracy values. We observe that with respect to the additional variables, we observe faster convergence, observe that the red plot reaches a very low cost function much faster than the black one. Similarly, we observe that as the number of layers increase, better accuracies are achieved for the case when z variables are introduced, corresponding to the case when z variables are not present. Therefore, the accuracy with the number of layers for the z is better, which is also observed with respect to different data sets such as RC, Dexter, Gisette, Madelon, and MLIS. Finally, we conclude that for a layer-wise optimization problem that we proposed, a layer-wise optimization approach that we proposed has several advantages. This highly scalable neural network approximation performs several advantages. The non-convex optimization problem has been split into multiple optimization problems. Each of them are probably convex. The vanishing gradient problem doesn't exist anymore because the gradient at each optimization problem is only a function of one layer. Therefore, the number of layers do not impact the learning scheme. But the big drawback of this approach is the fact that additional computational complexity is introduced because of these new variables, and parallelization techniques can reduce the impact of these computational complexities. One such parallelization technique was presented in this paper. However, because of lack of time, we are not able to discuss this.
Yeah, this is a really fantastic talk. Let me see if the participant, yeah, we do have the main speaker here, so that's great. So a few questions I had was, sorry, one sec. Yeah, a few questions. So in the step where you are learning the locally convex models for the modified Z based on the previous Z, based on the penalty, are you learning just the Z or also the Z and the weight function for that particular convex block?
So we have to learn both.
Right.
So the thing is, at the first step, you have to make sure your data is learned. You have to make sure that the Z mimics the data. And the second step, you can learn the weight. So it will be an alternative optimization where once you go through multiple iterations of updating Z's, Z converge, and then you update W's, W converge, and then you go to the next chunk of data.
Sure.
So for every data, you will learn a new Z.
Got it. So here you're also assuming then, correct me if I'm wrong, for every chunk, so you're still assuming your losses with respect to the prediction Y. So you are having a loss for each chunk.
That's the beauty. For each of the block, you get a separate loss. So your Z's will do the job of trickling down the value of the Y and Y hat all the way to the bottommost layer. So you are not essentially having a target for each loss. The target for each layer is given by its Z, not by the Y at the output. So you can essentially put these things in separate nodes, and you never have to communicate the weights. You never have to communicate the data. You only have to communicate the Z values. That's required because Z doesn't know what to learn otherwise.
Sure, of course. Yeah, this is very interesting. Yeah, there's a lot of implications to this apart from the parallelism that you're doing. So that's great. What else? One other question was, have you tried this with the fully connected style neural networks, or also have you tried on like image or text kind of the convolutional networks or something?
Both. So the only difference that makes is if, let's say, you are using a convolutional style image, the Z takes the space of an image, and you are numerically learning. I mean, Z is a matrix then, and you are numerically learning a matrix, which is obviously a harder learning problem than learning a vector. But we have tried both.
Okay. Okay. Very cool. Yeah.
That result with respect to MNIST, if you saw in case of both as an image and also as a vector.
Okay. Yeah. Fantastic. Yeah. We will certainly reach out.
However, you can always vectorize a matrix and do it. We have not tried with 3-channel images. That is not something we have tried. So
Okay.
not sure how it will work out there. We have not tried with 3-channel matrices.
I see. I see. Yeah. Okay. Yeah. This is fantastic. Yeah. Thank you very much, and we will engage.
Thank you. I'm sorry if it was a little too fast because I had to squeeze a lot of material in 15 minutes, but thank you. Thank you.
I think this was very well done, actually. So this is a very good presentation. Yeah. Thank you very much. Okay. So we move along to the next slide, next talk. So next talk, we have Divide and Conquer, Leveraging Intermediate Feature Representations for Quantized Training of Neural Networks by Ahmed L. Take, Pranay Pilligundla, Alex Cloninger, Hadi Ismail-Sareh from UC San Diego.
Hello, everyone. This is Ahmed Thaqib from UC San Diego. Thanks very much for the invitation. So I'll present our work, Divide and Conquer, Leveraging Intermediate Feature Representations for Quantized Training of Neural Networks. So the core idea of this work relies on 2 main insights. The first insight is the fact that in the context of neural networks, depth is a fundamental aspect of representation learning. And as it's commonly known, earlier layers learn low-level features, and as we move forward in the network, we learn higher and higher levels of abstractions. So for example, we start by learning edges, then parts, all the way to complete object models by the end of the network. So neural networks are really all about learning multiple levels of features. The second insight is the concept of knowledge distillation. And knowledge distillation is a generic approach which aims to reduce a large model down to a simpler or smaller model in a teacher-student paradigm. So combining these 2 insights, basically the hierarchical learning aspect of neural networks, which yields multiple intermediate features across the network, and by leveraging the concept of knowledge distillation, we define a new approach focusing on teaching the knowledge of such intermediate features to a corresponding quantized student. So more specifically, given an input image, the typical training procedure for a neural network is through an end-to-end learning process. Here, instead, we propose to divide the pre-trained neural network into multiple subnetworks, and we leverage the intermediate feature representations to feed into a newly defined regression losses at the interfaces of these subnetworks. So this way, DCQ provides a sectional multi-back propagation algorithm that leverages multiple instances of knowledge distillation and intermediate feature representations to teach a quantized student through a divide and conquer strategy. Here is the training procedure. So given a pre-trained full precision network, we split the pre-trained full precision network into M sections. For each section, we construct a subnetwork containing all the sections preceding and including the current section, as you can see. And for each subnetwork, so you can think of each of these subnetwork as independent training task. Now, for each of these subnetworks, we quantized all layers in the current section with the desired bit widths and set their weight parameters as trainable. So Q here refers to the weights being quantized, and T refers to the weights being trainable. Similarly here, the H refers to high precision weights from the pre-trained model, and F refers to freezed, means we don't train them. So we quantize all layers in the current section. with the desired bit width and set their weight parameters as trainable. And we freeze the parameters of all the preceding or the remaining layers in the preceding sections. And then we perform sectional pack propagation for each subnetwork. Finally, we merge the quantized sections from each subnetwork training task to form the fully quantized student network. This algorithm outlines the step-by-step procedure for DCQ, putting together all the steps described in the previous slide. So in high level, we have a split phase followed by a merge phase. Looking into some experimental results, here we compare plain Dorefa versus Dorefa plus DCQ for binary and ternary quantization. Experiments on various benchmarks show that on average, incorporating DCQ improves the performance of plain Dorefa by around 21.6% and 9.3% for binary and ternary quantization, respectively. Additionally, we show that incorporating DCQ to existing quantized training methods leads to improved accuracies as compared to previously reported by multiple state-of-the-art quantized training methods. As such, this shows that DCQ acts as an auxiliary approach to boost performance of existing training techniques by applying whatever the underlying training technique or method, but in a stage-wise fashion, with defining a regression loss per stage. Now, in terms of ablation, we look at some of the loss analysis for DCQ. So, as we mentioned, DCQ is basically DCQ divides the original classification problem into multiple regression subproblems by matching the intermediate feature maps. So when it comes to regression, there are multiple loss formulations that can be utilized. Here we examine three of the most commonly used regression loss formulations, namely the mean square error, mean absolute error, and Huber loss, which is a sort of a combination of both MSE and MAE. So this figure shows loss visualization while matching the intermediate feature maps. The first row shows the loss before using DCQ training, while the second shows after DCQ. Each column is for a different loss formulation. So the figure shows that first, the loss, or basically the amount of redness, is significantly decreased after incorporating DCQ as a result of regressing the quantized intermediate feature maps directly to the full precision counterpart. We also observe that this behavior is consistent across the different regression losses. However, based on our experimentation, the mean square error seems to be the most effective during the intermediate learning process. Here we show the actual feature maps before and after DCQ. And as we can see, the feature maps after DCQ almost match the full precision counterpart. And this primarily, again, is a result of directly regressing the feature maps to the full precision counterparts, which is the reference in this case. On another side, from implementation point of view, one more advantage of DCQ is that it enables parallelization towards training quantized networks. So since DCQ applies knowledge distillation through sectioning, it enables training each section of the sub networks independently and in isolation to deliver a quantized counterpart for the teacher, which can occur in parallel. In terms of memory requirements or overhead, with simple analysis compared to the conventional end-to-end training, DCQ only needs an extra set of weights divided across the training nodes, which is the same as any other conventional knowledge distillation approach. Nevertheless, DCQ does not impose any extra memory requirements on the activations. We also conducted some theoretical analysis, and here we briefly present a couple of these theoretical results. So one issue that arises as a result of the strategy of splitting into sections and training each section separately is the accumulation of error residuals through sections, which may impact the overall performance of the proposed technique. Here, we theoretically drive an upper bound on the total accumulated error across the resulting subnetworks after splitting using a chaining argument and utilizing Lipschitz continuity. Theoretically, we show that even though there is a non-zero error after each section or subnetwork, when you chain the errors together, you can still bound the error and bound the overall misclassification probability. The theory is built on a chaining argument where you bound the error from layer, say, k-1, and that bound feeds into bounding the error at layer k. For more details, please refer to the paper. In conclusion, we developed DCQ, sectional multi-pack propagation algorithm that leverages multiple instances of knowledge distillation and intermediate feature representations to teach a quantized student through divide and conquer. DCQ achieves significantly higher accuracy compared to the state-of-the-art quantization methods by exploring a new sectional approach towards knowledge distillation. Finally, divide and conquer is a very basic and universal engineering principle that is commonly and widely applied across a variety of systems. DCQ here is a procedure that extends such effective concept or principle to the training of quantized neural networks. Thanks very much for your attention.
All right, thank you very much. The questions can be asked on Slack. So we have a time zone difference. So sounds good. The questions can be asked on Slack, and the others will get back to you and open and follow up on your thread when they're back online. Okay, so the next talk is Split Easy, a practical approach for training ML models on mobile devices. This is by two undergrads, Kamalesh Palanisamy, Vivek Khimani, and their co-authors Moin Hussein Moti, Dimitris Chatsopoulos from NIT Trichy, Drexel University, Hong Kong University of Science and Technology.
Hi, my name is Kamlesh, and today I'm going to give a talk on our paper, Split Easy, a practical approach for training ML models on mobile devices. This is a joint work I did with Vivek, Moin, and Dimitris, and our paper will be appearing at the ACM Hot Mobile Workshop. So what was the motivation behind doing this work? So as you can see in this image, there are quite a number of devices. A Raspberry Pi, which you can consider as an edge device, and a low-end mobile phone to a high-end mobile phone, and then a GPU. So when we take a common deep learning models, most of them are easily able to run on a GPU. But then when you take these four devices, they are not easily able to run on them. And when we want to bring machine learning from research to production level systems, this causes a big problem because most of these mobile phones are the production level systems where we want our models to run. A few initial work has been on reducing the size of the model, such that they are able to run on mobile devices. Models such as MobileNet and SqueezeNet have been very popular ones that are easily used for running on mobile devices. And as you can see in the graph here, of the top one accuracy on ImageNet versus the number of operations, MobileNet and SqueezeNet reduce the number of operations compared to the larger models by nearly 10 times. But the problem is that they have accuracy of only around 70%. This is not bad, it's a decent performance, but then still it's not up to the level of the larger counterparts, which have more than 80% performance. And this brings the need for finding more techniques that will not let us compromise on the performance, while at the same time it will keep the number of operations low on the device. And this is where split learning comes as a solution. But however, I would say split learning is a near perfect solution for this problem. It's not a perfect solution because there are still some problems with split learning that we need to solve before we can say that split learning is a perfect solution. And this is what we try to do using Split Easy. Split Easy is a framework which you can easily use to integrate in your applications especially on mobile devices, so that users can experience split learning on real time. And this is one of the first such frameworks to do this on mobile devices. And while developing a framework, we faced quite a number of problems, but the main one was with automatic differentiation. So automatic differentiation is the algorithm which is used to run our neural networks. It works by creating a graph of the variables and the operations in the neural network. And during the forward pass, it goes from top to bottom, and the backward pass, it goes from the bottom to the top of this graph. But then in split learning, as you know, we cut the network between the mobile and the server. And because of this, there's a discontinuity in the graph. And this discontinuity makes this part of the network not know what is going on here. So what it essentially means is that the gradients will not be able to travel from here to here. And because for the gradients to travel, it needs to know what is going on at the final, that is the loss here, so that the gradients are appropriately sent to the weights. And for this, many papers have proposed a solution, but those solutions work on a single language like Python or only in a single device. And they didn't work when we actually took a mobile device that was using JavaScript and a server that was using Python. And we tried to integrate the solution into our solution into Split Easy. And basically what our solution does is, and before I go and explain our solution, let me give a small overview of the notation. So let us consider the first split A, split B, the second one is split B, and split C. Split A and split C are on the mobile device, and split B is on the server. We use a two-split setting because that is the most common use case scenario, because this protects the privacy of the user by keeping both the input and the target on the mobile device. So these are the activations of each of the layers of the network, and these are the weights respectively. The update equation for the weights are given here. I'm not going too much deep into the theory because the time is less, but you can read more about this on a paper. So the first update equation is Zt is equal to Zt minus 1 minus eta dou L by dou Zt minus 1. So this is based on the loss L for the final term. This loss L can be a cross entropy loss or a mean square loss. And eta is a learning rate. So this can be done normally because split C is on the mobile device and loss L is here. But then when we go to this split and the update equation for W, we find this part dou L by dou Wt minus 1. And this is the one that is difficult to compute because W is not aware of the loss L because of this discontinuity. And we need to somehow ensure the normal training process despite this. And for this, what we do is that we add a new loss function to split A and split B. Essentially, what we are trying to do here is that we want split A and split B to reduce their own loss, find the own optimal solution for their output A and C respectively. And in this manner, we will be able to find a global minima for both these networks such that still the final loss L is reduced. And the loss function L is basically C hat minus C, the whole square, which is a mean square loss. And the C hat is C plus dou L by dou C. So what this basically means is that the target for model B is to find the output C plus the gradient of output C with respect to the loss L. And this gradient, we can derive it from the final mobile device and send it over the network. Although this adds a further communication cost, this seems to be the only way for us to actually create a solution that will enable us to update the weights of V and W. And similarly, we do this for the weight U. And and as you can see here, I'm not explaining this theory. When we substitute the loss LB in the update equation of WT, we are able to get the final update equation similar to the one when we use a normal loss L. And by this way, in this manner, by adding a new loss L, we are still able to replicate the normal training process for W. So the theory worked out, but then we still needed to empirically check it, and we used VGG and DenseNet on the CIFAR dataset to check whether the normal training process and the modified training process gave similar results. And as you can see here, the test accuracy was a number of epochs. The normal and the modified training process seem to follow a similar curves. So the modification which we did not affect the training process in any way. Then the next experiments which we did was on the device, that is an iPhone XR. And we did this using the ImageNet dataset. So the first experiment was to run all the common networks that was available, and we reported the time that is required to run a batch versus the number of parameters. So here I want to make an important point as to why we are using time and not other metrics such as flops that are being reported by other papers. Because flops being low is very obvious. We know that when you offload most of the compute to the server, the number of flops is going to be less on your mobile device. But then the time is not necessarily will not necessarily be less, because the time depends upon number of factors. It depends upon your device. It depends upon the communication, whether you are using more optimized algorithms, etc. So reporting the time required to run a batch is a more better metric to see whether your algorithm works properly rather than just the flops. And as you can see here, despite the number of parameters increasing by twice or thrice, the time required to run a batch remains within 0.5 seconds. This is because most of the specialized layers of the network are in the server, and the mobile has a common set of layers. That is, most of these models have a common convolution and max pooling layers, which are in the mobile device, which leads to this common runtime. So the runtime here is only dependent upon the communication and then the number of layers that's present on the mobile. And this naturally brings the question, where do we cut the network? And we did a case study with Inception ResNet v2. And as you can see, in the case of Inception ResNet v2, it has a few convolution layers followed by a max pooling layers and a few convolution layer followed by max pooling layer. And when we cut the network after the final max pooling layer, the time required is low. This is because the size of the data is very reduces by nearly 4 times after the final max pooling. But then when we cut it after the first max pooling layer, it increases and so on. This is because the data size will be more, so the communication time increases. Why are we still reporting this? Because this seems like a very obvious fact. So what we want to say here is that some mobile devices will not be able to run even 3 layers of convolution in their device. So in those cases, the application developer needs to make a choice, and this can be done algorithmically based on the network device's network speed and its computation available to choose a location where to split the network. And we want everyone to be aware of this algorithmic choice which they can take while developing a split learning solution. And then the final one is, does the location of your server matter? This is an interesting study which we did. And as you can see, in the case of a home network, the time required is less. And in the home network, home server situation, the server and the mobile device are in the same network. And AWS, as you know, has lot of regions, so the time taken will be similar irrespective of where you are in the world. And the special case of a university server, since the university server was in a private network, we had to use a proxy network. And since the proxy network increased the distance for the data to travel, the time taken also increased. As you can see, there is a linear increase in the time taken depending upon your server choice. And this is what we request most of the papers to do. Please report the location of the server so that it becomes clear as to whether there's any actual progress in your algorithm, or it is because you did a few hacks of keeping the server in the same network that your time is low. And by doing this, we can keep track of progress in split learning algorithms. And once we are able to do this, we can then slowly come to a perfect solution for split learning. Because the main problem in split learning, as we have seen in these slides, is the communication. Once we are able to reduce the communication time, split learning will be a perfect solution, much better than designing models tailored for mobile devices. And that's what we wanted to do with Split Easy. And we have written a lot about this on a paper, which you can check it on archive or on the STM website. Thank you and have a nice day.
All right, that was a great talk. I think Kamlesh is available online for direct questions. So yeah, this was great. I have 2 quick questions. So what was the application you had in mind, like in this diagram where you have a mobile A that hosts the data, but the solution for the prediction ends up at another mobile B instead of at the server? So is it some peer-to-peer interaction that you had in mind that mobile phones are doing to help each other?
I didn't exactly get you. Like,
yeah,
you're asking.
So typically, I mean, there are many ways to do this, right? So one thing that we typically see is the label occurs at the server. The label gets predicted at the server. But here you are going via the server where the label gets predicted at the mobile phone C, right? So was there a motivating application for that?
That the reason why we did that is because like we wanted to do a completely private setup where both the targets and the inputs are like in the user's device. The server is aware of nothing else except the middle portion of the network. So that's what we wanted to test out. I think this was also mentioned in one of your previous papers about splitting it twice so that the labels are also on the device. Yeah. So we wanted to focus on this because I think this solution, the performance will be easier on a single split case also, but we wanted to like check a double split where both the inputs and the targets are like on the mobile device.
Got it.
So
Yeah.
for a complete private.
Yeah, I see your motivation. Yeah, but I guess in a societal situation here, mobile A and C are getting into some sort of a pact to help each other. So
no, by the way, the model A and C are in the same device. They aren't in different devices.
I see. Okay, so then it makes total sense. Then it's a perfect U-shape, the one we had in our paper. Okay. I thought the mobile A and mobile C are different. The model A and model C are in different mobiles.
I just named them as model A and model C. They're in the same mobile.
Okay, perfect. That clarifies. The other question I had was when you were measuring this very nice communication times and stuff, were you just using MPI or some SFTP for setting up the network communication, or were you using like something like Harvard or like a something that is an infrastructure or framework that exists already for doing distributed?
No, like we didn't go very deep into it because I was like just doing, this was mostly done on a normal mobile phone. So it's just a normal server, like post get request based communication, a single line, a single thing. It's not distributed. And so that's kind of like a future work now to check it more.
Got it.
How it works as a system. Yeah.
All right. Yeah. Very cool. Yeah, this is great. So let's keep moving. Thank you, Kamlesh.
Yeah, thank you.
Hi, my name is.
So now we have a lunch break, and we convene back at 1:30 p.m. And at 1:30 we'll have the final keynote of the program by Peter Kairos from Google. So see everyone at 1:30 p.m. EST. Hey, Peter.
Well,
Yeah. I was just trying to see if we can listen to your audio. It looks good. So we start in 3 more minutes. So.
All right. Okay, take your time.
Cool.
Should I try to share my screen?
Yeah, let's do that.
It says it will stop others from sharing their screen. Is that okay, or?
Yeah, you can. Yeah, that's perfectly okay.
All right. Okay.
Yeah, this was more of a placeholder during the lunch break.
All right.
All right. Yep, we are live, and yep, welcome to Peter Kairuz. We're very excited for his keynote talk, and he's a scientist at Google. So it's all over to Peter.
All right, sounds good. Thanks so much. Hi, everyone. I'm Peter. I'm a research scientist at Google, and today I'll be telling you a lot about federated learning and privacy for federated learning. I'm going to be presenting the work of a lot of people on my team at Google, so I hope you'll like this talk. So before I jump into the details of the talk, I wanted to try to touch on a definition of what we mean by federated learning. So we view federated learning as a machine learning setting where multiple entities, these are clients, they can be phones or institutions, hospitals, banks, so on and so forth, they collaborate together in solving a machine learning problem. And they do so under the coordination of a central server or a service provider. The most important thing about federated learning is that each client's raw data, those are the training examples and the labels, is stored locally, and it's never exchanged or transferred. It's not exchanged with other clients participating, and it's not exchanged with the server that's orchestrating the computations. Instead of that, only focused minimal updates that are intended for immediate aggregations are used to achieve the learning objectives. And so I'll dive a little bit deeper into this. But really, if you want to learn everything about federated learning, there's this very nice survey about recent advances and open problems. You can find it on arXiv. You can find it on the web. It's a large effort by 58 authors. A lot of the authors have participated in organizing or even speaking at this beautiful workshop. So please check it out because it talks about many different aspects of federated learning. But in this talk, I'm going to be mostly focused on cross-device federated learning, which is a special case of federated learning. This special case of federated learning is about training on a very large fleet of devices. So in this setting, we have, you can think of the participating clients as phones or tablets. You can think of them as small IoT devices, but there's a lot of them, millions, hundreds of millions, if not even billions in some settings. And the server is trying to orchestrate the computation because each of these clients has a very small data set, tens or hundreds of training examples, and they're all collectively trying to learn one single machine learning model. And so this server is trying to orchestrate the computation back and forth between these clients in order to train this one model. And at the end, there's an engineer that's trying to inspect metrics to make sure that the model does a good job, works as intended, improves on the state of the art. And finally, once that model is learned, it's deployed on a large fleet of devices. This is the last stage in this slide. All right, so one class of algorithms that has been around for a while that is very popular is federated averaging algorithms. And in this setting, what we do is on device, we take the training examples. Those are essentially the examples with the labels. And we run multiple steps of stochastic gradient descent. We do that locally. And we can do multiple epochs, multiple passes through the data sets, or not. This is up to essentially the orchestrator to tell the devices how many runs to go through their local data sets. But we apply stochastic gradient descents for some number of iterations locally, and then we get an updated model because we've done this improvement on device. And once that updated model is obtained locally, it's sent back to the server where aggregation happens. All the clients that are participating in a round send their updates, and these updates are averaged together in a weighted fashion. You can assume that the weights are equal or non-equal weights based on how many training examples each device used. And you can iterate back and forth. You can do many, many rounds until you get good metrics. In other words, until the model has converged. So this is essentially the space of algorithms that we are going to be concerned about for this talk. And the focus of this talk is going to be on privacy. So what I've just said, which is presenting the system, is a great step forward. But let's take a look at what we mean by privacy. So there are three main questions that for privacy we need to ask, and we need to kind of understand very carefully. These are the why and the what and the how of using data. So the why is, why are we using data in first place? Does the user understand that their data is being used for a specific computation? Do they approve of this use? And this is a very important basic question that any service provider and any service should try to articulate very carefully with its users. The second question is the what. In other words, it's really, kind of trying to make sure that there's limited influence of any individual. So what is being computed? Are we training a large model that's going to overfit and memorize unique training examples? Are we training a very small model that's only going to capture holistically some population level statistics? It is important to know what is being computed. What is that query or computation that we're conducting on users' data? Because we can know specifically to what extent does this computation leak sensitive information or overfit or maybe overlearn or memorize. So that's important. And finally, the third question is the how, essentially. How and where does the computation happen? Is the computation happening on user devices? Is it happening on the server? What's happening on the user device? What's happening on the server? And who gets to see what part? Is it encrypted or not? What kinds of technologies are being used for these computations? Are they happening in a secure enclave? So on and so forth. So these are the three very important questions that we need to tackle when we talk about privacy. And perhaps it's obvious to you that the why question is a little out of scope for specific technologies, especially the ones that I'm going to be talking about in today's talk. It's more on the policy side of things. It's more on the UX, UI side of things, and more on regulation side of things. But the what and how tend to be very aligned with technologies that we can build, and especially those that I'm going to be talking about today. So let's try to dive a little deep on those two axes. But first, keep in mind that the system we are talking about, this federated learning system, is pretty large. It has many components to it. There's the clients that participate in the training. There's the server that does the orchestration. There's the engineer that has requested the model, that does the assessment of the model by looking at metrics during the training. And then finally, there's the deployment phase, where you have perhaps a very large fleet of devices that are going to receive this model and use it for prediction tasks, for classification, so on and so forth. So this is a very complex system. So in order to try to better understand the what's and the how's of privacy, we need to really focus on the various actors in this system. So in other words, we need to try to ask ourselves the question, what private information might each actor learn if they've access to information? So here's one example. For instance, what do these devices have access to? They're receiving a model from the server. That's what the server has learned so far. And they have their own local data, and they're going to compute on that model. By inspecting that model and poking it, what can these participants really learn from the data? If there's an adversary sitting on the network, listening to all the communication that's going back and forth, what can that adversary on the network observe? The server is receiving those updates back from the clients. What do those updates contain in terms of sensitive, personal, private information? The engineer is seeing the released models, kind of these model iterates, and the metrics. What do these metrics or model iterates leak as in terms of sensitive information? And finally, when we deploy that model, we're probably going to deploy it on a really large fleet of devices. So this final deployed model, what does it leak in terms of private information? So we really need to understand those pieces, and those pieces tend to be fairly complex. And we can start talking about threat models and technologies that help us mitigate the privacy for those threat models. And really, in order to have a privacy in-depth analysis, we need to look at all these questions simultaneously. We can try to take them apart, try to understand them, and then tackle bits of this story simultaneously. So as I was saying before, we can use different technologies that have different guarantees for different threat models that might arise, depending on what actors may be compromised and what access to information different actors might have access to. So let's start with this very basic threat model, where we assume that the, say, adversary is sitting on the network and trying to observe the communication back and forth between the server and the participating clients. For this one, if we use encryption on the wire, end-to-end encryption, then we can ensure that anybody who's spying on the communication will not see the actual model updates that are being exchanged across rounds, because everything is end-to-end encrypted. So if we take that message, we're not going to learn much. Now, if we go to a more complex threat model, here we ask ourselves, what private information might the server have access to? This is slightly more complicated because the server needs to, in some sense, see those updates. Then there is a technology that can help us to ideally hide everything from the server. And this is called local differential privacy. In the workshop today and yesterday, there's been a couple of talks on differential privacy. I'm not going to dive deep into the definition of differential privacy, no math in this talk. But what really local differential privacy is about is the following. What you do is on device, when you compute the update from the local data set, you clip that update. So this update is a gradient. You can think of it as a vector. And you clip the L2 norm of that update. This is, in some sense, done to bound the contribution of that client into the training process. And then, in addition to clipping the norm of that update, you add Gaussian noise to it. You can add different kinds of, there are different types of noise that you can add, but Gaussian noise works. So imagine every participating client would do the training, then clip their update at the end of the training and add noise to it. So they would send a noisy update from their device back to the server. So in some sense, if every participating device follows this procedure, they're fuzzing up their updates to kind of get privacy guarantees, then you can see that if the adversary not only has access to the server logs, seeing all these exchanged model updates, but if it has access to everything else, you get protection from this technology. It's a pretty strong, if you want, scheme to achieve privacy, because it gives you protection against many different threat models, as I'm showing on this slide. Now, if we go for a slightly weaker adversary, if we go for something like, I trust the server, but I don't necessarily trust the engineer that's requesting the model and checking those model iterates and the metrics, then we can do something slightly different. We can opt for central differential privacy. This is, again, based on differential privacy, but it's a different model of differential privacy. So here, in this case, what we can do is we can still clip those updates locally on the device. So this is exactly the same step as I showed you before when we talked about local differential privacy. But now what we do is, upon aggregating those clipped updates, the server itself would add the noise. Notice that here, I'm adding noise after the aggregation on the server instead of to each individual update on the client. And it turns out, without getting into any math, it turns out that for this approach, we can get a much, much better accuracy. So compared to local differential privacy, where we add the noise locally on the device, this approach helps us to achieve a much better accuracy, of course, at the expense of having to trust that the server is going to add the noise. And the server is going to delete all the logs that it's seeing. It's going to aggregate, and once it aggregates, it deletes the logs and adds noise to the aggregate, so that everything else is now protected with differential privacy noise. Now, to implement this framework, there are so many details that you have to worry about. You should worry about adding the right noise, a secure implementation of the noise, how we do privacy budgeting, how do we calculate and track the privacy budget. And so at Google, we've designed a library for TensorFlow that trains models with differential privacy, and it helps you add it very easily into their training loop, and it helps you also calculate and track the privacy budget. You can find the white paper of it on arXiv. I'm showing it here on this slide. If you want to read more about this, the science of this library, of how it's built. And with central differential privacy, what we're saying is that there's going to be a segment of the actors that are sort of trusted, but there are others, for instance, the analyst, the engineer that has requested the model, that's inspecting those model iterates and the metrics, and any downstream, if you want, actor, like those phones that are going to receive the model once it's deployed, the adversary might have access to all that information. And central differential privacy gives you strong privacy guarantees for this type of an attacker, for this type of a threat model, which is pretty cool. Now, you might say that this is great. Local differential privacy is designed for a stronger threat model. Central differential privacy is designed for a weaker threat model. Can we try to get the best of both worlds? Because under central DP, as I mentioned, we're adding noise only once after aggregation, so we get better accuracy with it if we train with central differential privacy. Whereas for local DP, because we're adding noise for each update locally on the phone, we tend to get less accuracy. So one natural question to ask here is, how do we try to kind of get the best of both worlds? The stronger privacy guarantees to some extent, and the better utility guarantees to the best extent possible. And it turns out that yes, we can do it. There is a notion that sits right in the middle. It's called distributed differential privacy. This essentially is a little bit of both, and we'll see it in a bit. And the core idea of distributed differential privacy is not too new. It goes back to 2006. There's this beautiful paper, Our Data Ourselves, that kind of pitches the idea of using cryptographic tools in order to try to bridge the gap between these two notions of privacy. So the core idea here is what we're going to do is we're going to rely on cryptography or secure hardware, so either secure enclaves or secure multi-party computation, in order to combine local differential privacy or local-like differential privacy with these cryptographic primitives in order to get the good accuracy and good utility that we sort of want, and in order to try to give protections against a threat model that may have access to server logs and all the other downstream actors. So let's see what we're trying to do. To be very precise, what we're really after is, we use a technology that's going to give us, slightly stronger privacy guarantees as we walk our way down into this picture. And as you can see, so we want the server to get some protection, some formal privacy guarantees, and we'll talk about it in a bit. And then those guarantees would get stronger as you move away. For the analyst and engineer that has requested the model, you get stronger privacy guarantees. And then the strongest guarantees we can give would be for the very large fleet of devices that are going to receive this model. So this is how we're going to do it. So notice on this slide that I'm still clipping and adding noise locally to each device. But so this might look a lot like local differential privacy. The only difference is that now I will add a lot less noise. So instead of adding a lot of noise locally, in order to achieve a certain differential privacy bound, in this way of doing things, I'm going to add much less noise, so that upon aggregating all these noisy updates, I would get on the server the right amount of noise that I would have otherwise added to get a central differential privacy guarantees. And because the noise that's added locally is not enough to get a good privacy guarantee, we should ensure that the server cannot inspect that noisy update that's coming from that particular client. And this is why we rely on cryptography to do secure aggregation in the middle. And so really here, the combination of local noise addition and this secure aggregation primitive, it's a cryptographic multi-party computation primitive that prevents the server from inspecting each individual update. This sort of combination allows the server to only see the aggregate plus the right amount of noise that is needed to get the right privacy guarantee. So let me dive a little deeper into it. And there are challenges here. And the challenges are these secure aggregation primitives that are used in practice, they, because they are cryptographic protocols, they operate on a finite group, meaning that all the computations are modular arithmetic computations done over a finite group or a finite field. They have a, everything has a finite size. So we cannot just add Gaussian noise, continuous Gaussian noise that we're so used to, and just assume that if we add a bunch of Gaussian noise on a bunch of clients that are participating in a round, once you sum them, you're going to get a Gaussian noise at the end. So, and there are other challenges, because if we switch to using something like the discrete Gaussian mechanism, first of all, it has infinite tails. And second, when you add multiple discrete Gaussian random variables, you're not going to get a discrete Gaussian random variable. This is somewhat of a surprise. At least it was a big surprise to me when I first learned about it, because we're so used to when you sum Gaussian random variables, you get a Gaussian random variable. But it turns out that in the discrete analog, in that discrete space, this result does not hold anymore. So you have to be very careful about the analysis that you make. And we sort of want mechanisms that allow us to do very tight privacy budgeting, because we're going to run this system many rounds in order to get the model that we want at the end of the day. So we want to be really good at how we calculate and track how the privacy parameters evolve with time. And so here's one way of doing this. We're going to use a version of the discrete Gaussian mechanism. We're calling it the distributed discrete Gaussian mechanism. I'm going to skip a lot of the details. You can find the paper on arXiv if you want to read more. But essentially what we do is we take those model updates. Xi here represents the model update that was computed on the client. And we do this clipping, the L2 clipping that I talked about in this talk previously. But after we do the clipping, we discretize the clipped update. So this is a vector of floats. You can think of it as vector of real values. And we're going to move from real values to discrete values, if you want. And I'll touch a bit on how we do this discretization. And then we add discrete Gaussian noise. But after we add the discrete Gaussian noise, which has infinite tails, we do a modulo clipping operation. So we essentially limit the precision over which we are operating. And once we do this modulo clipping operation, we get elements that are in a finite field or in a finite group. And those elements in the vector can now be used on top of an existing secure aggregation scheme. So just to tell you a bit more about how we do this discretization, because it turns out it's very important to do it carefully, what you should do is you should scale the data appropriately, and then you apply a rotation on the scaled data. This rotation is a random rotation that helps you to flatten out the vector. It allows you to make sure that all the coordinates of the vector are essentially, they have the same range. We don't have some entries with a large range, other entries with a small range. And then you do randomized rounding. You go from real quantities to discrete quantities using conditional randomized roundings. And I have the details in this box that I'm showing. No need to really dive into the math of it. It's in the paper if you want to learn a bit more. And on the server, after we apply the secure aggregation box, now that we have elements that have been clipped to be in a certain finite group, we can just use off-the-shelf secure aggregation as a black box. We will do the opposite chain in order to invert the discretization. So we would start by dequantization. We go from discrete to real quantities, and then we do the inverse rotation that we applied, and we do the inverse scaling. Now, obviously, there's so many details that I've glossed over. The end-to-end privacy analysis is highly non-trivial. How we compute the epsilon and how we do the privacy budgeting across rounds. I invite you to look at the paper if you want to see how that's done. But I wanted to show you quickly some results. This is one very popular benchmark dataset for federated systems, especially for cross-device federated system. It's called the Federated EMNIST dataset. And it has about 3,400 clients in total. So what we're doing is we're doing training with 100 clients per round. And we're training a model with about 1 million parameters. So it's not a very small model. And what we did is we trained it with centralized differential privacy using the continuous Gaussian mechanism. And then we trained it with this new approach that I just presented, this distributed DP approach. And as you can see on the slide, that if we have enough communication bits, so we need about 14 or 16 communication bits, we can get an accuracy that matches exactly central DP. And this is the beauty of it. Now, without having to add noise on the server, with just adding the noise on the client and relying on this secure aggregation cryptographic primitive, we can get stronger privacy guarantees for the same accuracy. And in fact, in the process, what we have managed to do is we have also managed to improve the communication budget. Because now instead of having to send real values over the wire, which are represented with 32 or even 64 bits if they're floats, now we're only sending 16 bits values. And those are much easier to send. We get 4x or 2x reduction in the communication cost. We did it also for another data set. This is an even more challenging data set, Stack Overflow tag prediction. Here, the model has 5 million parameters. We have far many more users in the system. We have about 342,000 users in the system. And again, as you can see, when I compare training with central DP to training with distributed DP according to the approach that I just presented, you'll see that about 16 bits or 14 bits are enough to get the same accuracy. For here, I'm showing you for different privacy levels. And again, the details are all in the paper. So, in the interest of time, I'm going to end here. I'm just going to say that there are other topics of interest. Please check the advances in open problems in FL if you want to learn more. And please ask questions if you have any. Thank you.
Thank you, Peter. This is a very informative talk and a lot of good references. So yeah, there's certainly some active questions on the Slack channel. I'll just read them out. The first is from Chandra Thapa from CSIRO Data 61. Peter, any insights on the model size and the model type that have been used in cross-device federated learning? I think it's an open-ended question. Yeah.
Yeah, that's a very good question. So in experimentation and simulation, we have experimented a lot with various models, image models, language models, so LSTMs, convolutional neural networks. And as you saw here in the last few slides, I'm using 5 million parameters for the Stack Overflow. We use even larger models for next word prediction models. I'm using for this simple EMNIS data set a 1 million model parameter. So those are kind of the sizes for experimentation and simulation. In production, I can say that we've openly at Google talked about at least a few applications, such as next word prediction for Google Keyboard, and those models are larger for sure. But we've openly spoken about, for now at least, speech and language models. But you can imagine that we can do this for other types of models.
Very cool. So one more question is from Abhishek Singh. So does the SMPC plus the central DP combination that you provide in distributed DP, does that provide protection against both server and malicious client collusion?
Yeah, that's a very good question. So I'd like to go back to this slide essentially. It depends on what we mean by malicious client collusion. If those malicious clients are are trying to break the model, there's adversarial machine learning or robustness, that's a little outside the scope of privacy in some sense. There are interesting interactions between privacy and robustness, very exciting new papers recently in the literature, but that's a little outside the scope of this talk. If what we mean by malicious clients in the sense that those clients are not going to add DP noise, because notice that in this approach, we are going to decentralize the process of adding noise. If that is the question, then this is a very good one, and this is a spot-on observation. If those clients don't add noise, then the DP guarantee is going to be reduced, because we're decentralizing noise addition so that we get the right amount of noise upon secure aggregation. And so it's important to make sure that we have that right amount of noise. If somehow now a fraction of the clients are going to be malicious and they're not going to add their shares of noise, we're going to get something less at the server. And so this is naturally going to degrade the privacy, the central privacy guarantees that we can give. What you can do in practice is that you can assume that there's going to be a teeny tiny fraction of your clients that will not obey the protocol, maybe say less than 1%, 0.1% or 0.01% in a very large system like the one we use at Google. And then if you anticipate that there's going to be, say, 0.1% or 0.01% of your clients that are not going to add noise, you can, because you anticipate that, you can crank up the noise shares that the benign clients are going to add, so that in the worst case, you still get the least amount of noise required to give a certain privacy guarantee. So you can take that into account. And in our paper, if you look at the last section of our paper, you'll see a paragraph and a few experiments that are done, especially specifically on this setting, where we assume that there's a fraction of the clients that are not complying. They are not adding any noise.
Very cool. Yeah, they like your answer. Okay. Yeah, thank you very much. This was a very exciting talk.
Yeah, thanks a lot.
Of course, there's the Slack channel for offline engagement as well.
Sounds good. Thank you.
Thanks a lot. Much. All right, so I'm back to screen sharing on my side. And we are going to proceed with the next research talks. All right, so that was a wonderful talk. And moving along, we have a talk on split learning in the vertically partitioned setting by Abhishek, Ayush, Vivek, Ethan, Emily, myself, Ramesh, from Accuratio and MIT. Accuratio.
Hello everyone, I am Iker and I am founder and CTO at Accuratio. Accuratio is a startup that has developed the most advanced federated platform. Support for federated averaging, split learning, secure multivariate computation, and our work on vertical federated learning that I will be presenting today. Federated learning has been traditionally focused on gathering data of the same type from multiple sources while preserving its privacy. This setup is called horizontal federated learning and is pictured in the top part of the diagram. The most prominent example is the use case first published by Google in 2017, where they trained a model for next word prediction joining data from Android keyboard users. Vertical federated learning, on the other hand, is a setup in which two or more companies that share a common set of records, for instance users, want to combine their features to create a more complete model. For example, hospitals A and B may want to combine the clinical record of a patient stored in Hospital A's database with the CT scans of the same patient owned by Hospital B. In this slide, we can see one of the most common settings for split-and-driven vertical partition. In this scenario, we have two companies, A and B, collaborating to build a model over their common set of users. It's a U-shaped network since company B holds both a subset of the features and the labels, while company A only owns a subset of the features. Accuratio is providing additional privacy guarantees by acting as a middleman and providing some computation layers. Sometimes this middleman's role has nothing to do with privacy, and it's used just to offload the heavy lifting of the model training to powerful instances on the cloud, by putting the bigger layers of the model within it. This architecture is compatible with other privacy techniques, such as the distance correlation, no-peek, and secure aggregation mechanisms. Finally, as in any split learning setup, the deeper the cut, the higher the privacy provided. The main advantage of this method is flexibility. We can consider neural networks as modular elements and connect them in a high variety of manners. Alternatives to split and end for vertical partition learning include secure multiparty computation, homomorphic encryption, decision trees, and vertical support vector machines. Unlike split learning, due to the expensive cryptographic schemes, those methods face critical performance challenges and communication overhead. Usually, split learning is achieved by concatenating the output of the different participants. In this figure, we can see the usual setup, where we have K clients generating the intermediate feature maps S, which are aggregated before being fed into the server. Then the server computes the rest of the computation graph, performs backpropagation, and returns back the Jacobians to the clients, which in turn can update their local models. In our paper, we propose to switch this concatenation by other pooling mechanisms, such as max pooling or element-wise product. This can help cope with stragglers, since in a concatenation we absolutely need the output of every client before finishing a training step, while with other pooling mechanisms we can ignore some of the inputs and the output set of the pooling layer will still check out. We evaluated 4 different pooling mechanisms on 3 public datasets. Since the datasets are for financial cases and hugely imbalanced, we report loss, accuracy, and F1 score for every method. As we can see in Figure 2, the centralized model is the best one, which is to be expected since we are feeding it with all of the data. In a real case, the federated models would have access to more features and would have a higher achievable accuracy. Interestingly enough, all of the other methods achieve comparable performance, with the best option being max pooling by a slight margin. We believe our approach to train models with vertically partitioned data provides a way which is better suited to its specific challenges, which are different from those arising with horizontally partitioned data. To evaluate the effects of substituting the aggregation mechanism with one of the proposed pooling methods, we conducted some experiments with clients dropping randomly during training. These experiments were done in a setting with 4 clients, and in every iteration, between 1 and 3 of those clients' updates were discarded to simulate straggling nodes. The only way to achieve something similar to this with concatenation is by storing delayed updates for every client, and using those delayed updates whenever a client fails to connect. As the figure shows, in a setting with 4 clients, dropping 1 or 2 of them randomly on each iteration has a limited effect on the accuracy of the model. This is an interesting starting point for future work, since it would be interesting to analyze how to minimize the impact of stragglers with vertical split learning. In the paper, we also evaluated communication and computation complexity for our protocol. The communication size in a vertical split learning architecture is dependent on the size of the output at the clients. The computational cost, however, is dependent on the architecture and the size of the input feature vector at each layer. Bearing this in mind, in conjunction with performance trade-offs between different merging strategies, it is extremely important to know the details and the limitations of the specific use case in order to be able to propose the best training strategy. The neural network architecture splitting scheme, or the adjustment of the hyperparameters, can greatly change the speed and therefore the efficiency of the training process. To illustrate the experiments conducted in the paper, I'm going to show you a short demo of Accuratius platform where we performed them. Accuratius platform includes several federated approaches to train deep learning models on data from different sources. Today, we are going to show a practical example of vertical federated learning and how a researcher or data scientist can go from data to a production model. We have been focused on making Accuratius multi-cloud platform really easy to use. We don't want data scientists to turn into cryptography and privacy experts. Instead, we give them the tools to easily transform their current centralized TensorFlow models into federated models. In this demo, I'm going to show you how to get started using Accuratius federated learning platform by launching a project, connecting your data, generating, customizing, and training a federated model, and sharing the trained model. The first step towards training our models in Accuratius is going to be creating our project. Here, I'm looking at the main dashboard where we have 3 options. Quick Start launches a ready-to-go project with several demo datasets and models, and it's useful for new users. Get Started launches a wizard which helps set the most common settings for the project, nodes, and datasets. And finally, we have the documentation. In this case, I have already launched a project. If I navigate to the Projects tab, I can see my demo and a variety of other projects that have been launched by my colleagues. Associated to my demo project, I have 2 nodes representing a bank and an advertising company. Our goal is to design a model to analyze a bank marketing campaign with data from both the bank and the advertising company. Nodes associated to a project pull their data from their local data catalog or cloud storage. These nodes can be provisioned in any of the major cloud providers or on-premise. Every project has also a federated dataset associated, where the owners of the data can share the necessary metadata so that every participant can agree on a common structure for this data. In our case, we can see the datasets for both companies and the kind of features available on each side. If we go to any of the pre-generated scripts in this demo, we can run it and see the output. Here, we have built a neural network with the architecture presented in our paper, with 2 participants training a U-shaped network and a third party in the middle. As you can see, we have used TensorFlow to define the network and then imported some custom layers to make the model distributed. This model learns to detect if a specific user should be contacted in a future marketing campaign. Since we are using TensorFlow and expose the same APIs, it's easy to evaluate the model and see how the different features correlate with the output. Once our model is trained and meets our standard, we may want to launch it as a service. We can quickly set up a REST or gRPC API from our trained model. To do so, we need to load one of the safe checkpoints and generate a servable model. Thanks for watching our demo. There is a lot more we'd love to show you, so send us an email or give us a call and we'll be more than happy to help you.
All right, yep, that was a wonderful talk on vertical partition data to do split learning. Looks like Iker is also available currently on the call. Awesome. So,
hello,
yeah, so because we're also co-authors, we're just gonna probably motivate a quick comment from you. So it looks like you focused on a specific domain of data, like one kind of a business domain. But are you, is Akirato also considering any other domains in specific, or was this just a toy data choice of domain?
This is mainly the domain where we found most use cases, and that's why we focused on that, because it's a really, like, financial use cases are a really clear example for this. There are others, like, for example, healthcare, and there are lots of demos out there about those kind of use cases also. But we found most use case for us to be in the financial space. So that's why we focused the demo on that. But it's just a trial for this demo, and also for the paper, because it went well with the motivation of vertical partitioning, where you have two companies that want to collaborate, and it's more common in this kind of setups. For example, in healthcare, usually hospitals have more of a similar domain on the data they own about the patients, and with companies it's not like that, and that's why we focused on it. But we are open to other use cases also.
Very cool. Yeah. So one more question on the Slack. Let me read it out. Okay. In your demo, what all infrastructures for the cloud, like AWS, Azure, etc., are supported?
Yeah. Right now we support all of them. Like the four of them. We support both AWS, Azure, and Google Cloud. And we also support launching the nodes locally on premise. So all of the architecture is built on Docker Compose and Docker containers. So it's really easy to set up locally in your machine, or even in your own computer. You can launch a node and connect to the API. So it's pretty easy to set up.
Got it. Yeah. One more question in your context for this project. Is there anything to keep in mind while using some sort of private set intersection to figure out which are the rows that are common across the partitioned data sets?
Yeah, we usually need to, like, for example, when we are doing this private set intersection between different companies, it's usually helpful if they have already a joint venture before we start using federated learning, because it's easier to homogenize the data between both companies. Otherwise, as you mentioned, it may be hard to find the appropriate IDs on which to do the intersection. Since you can't look at them in plain text, it's pretty hard to make them look the same. But we can use several techniques as filters and other things that can be used to pre-process those IDs. And from the privacy point of view, the private set intersection, since the spline ID that we are generating, it's not reversible. There are no problems with privacy on the ID itself. The only thing you have to take into account is if the rest of the features for the user are pseudo identifiers. So if they identify uniquely the user, then you might have a problem. So you need some kind of key anonymity on those features to make sure that you cannot re-identify the user with those features. But otherwise, it's not a problem. The ID is safe on itself.
Got it. Makes sense. Yep. So yeah, thank you for the talk and for attending. So we carry on to the next research talk now.
Yeah. Thank you.
Thank you.
Hello, everyone.
All right. So the next one is on split learning for medical imaging in healthcare. Multi-center deep learning without sharing patient data. Martin, myself, Ken Chang, Jayashree, Rajiv Gupta, and Ramesh from MGH, MIT, University of Twente, and Brigham and Women's Hospital.
Well, hello everyone. My name is Martin Poirot, and last year I worked with the group at Media Lab at a very exciting project on the application of split learning in healthcare. You can find our article on arXiv. I'm currently doing my PhD at the Amsterdam University Medical Center, and I'm doing deep learning research on MR imaging for psychiatric patients. We are always looking for ways to improve our data, and with improve, I don't just mean increase samples, but also increase diversity. And that's why I got really excited talking about distributed machine learning and split learning, especially because it's gonna solve all of our problems, or at least that's the premise. Today we'll talk a bit about the background. First, I want to make the case that distributed machine learning can be really helpful in healthcare due to some facts about medical data. The second thing is that I want to introduce the concept of distributed machine learning because a better understanding of distributed machine learning will help us understand split learning. And when we have all the background, we can start thinking about the paper that we have on archive. We did a feasibility study of split learning in healthcare, and I'm going to show some applications that we made. So first of all, data. I already talked about it. Currently, I'm working with MR imaging, and we always have too few. So medical sample sizes are really small. When we think about deep learning, we think about these openly available large data sets. But in healthcare, there have been initiatives to open up large data sets, but there's never enough. And for it's just not workable to set up a new repository for every new research that you want to do. The second thing is that models trained on one data set can often not be used for others. So the solutions that we're coming up with might be very specific and might not generalize for new problems. And the third thing is when you wonder why, if we need all this data, why don't we just share it? Well, there's a lot of hurdles that we have to cross. There's a lot of laws to protect patient privacy. There's regulations to protect loss of control, because the data is actually an asset to the hospital. There's logistics. Some of these data sets are terabytes and terabytes in size, and a simple researcher might not have the location to store it. And lastly, there's ethics, because patients have to give consent, and we don't know, we cannot just hand out these data sets because we don't know what's going to happen to it. And the final number that I want you to remember is that only 2.9% of published papers on deep learning in healthcare includes data from multiple institutions. And that really hampers the application of these methods in healthcare, because we cannot thoroughly prove the reproducibility. So the second solution immediately that we come to, and that's for the topic of interest today, is distributed machine learning. Distributed machine learning basically means that we're not training in one centralized location. Instead, we're doing it distributedly. And there are several methods shown in the bottom left here, called cyclic weight transfer, federated learning, and split learning. And in the back of me, you can already see an image of how Google explains federated learning. And they have an example of you having keyboard data from Gboard, and that's of course sensitive data that you don't want to share with the rest of the world. So what happens is that your phone, when it's plugged in at night, trains the neural network, and every morning it sends an update that is that's aggregated at the Google servers. So in this way, training is happening distributedly. And the same thing is what we want to do with split learning, but in a whole different concept. Now we don't do all the training on the distributed devices, but we split up some parts and we send over the features in between. So you can now see in blue that some parts, and those are actually the more shallow parts, are happening distributedly, but the center is happening on a server. So this is another diagram. So you can see several hospitals here, and they send over features and gradients, but the data and the labels remain the same, or remain at the same location. So in this way, you can train models without having the data ever leave the premise. So now if we understand a bit about the background of split learning, I'm going to show you what we did in our research. We start with the research question, and that was in the first place if split learning was feasible, because every different application has totally different requirements. You can imagine the example of Gboard I just showed you. The phone can process relatively a large amount of data, so it's a pretty strong edge, or pretty a computationally strong edge device, but the data sent over, the models are maybe pretty small. There's millions of devices. So in healthcare, the tables are totally turned. We only have a few institutions that are probably collaborating on a single project. The data is really large, and the models are probably also going to be really large. So that's why we want to show feasibility of split learning. And our methods are to build a split learning testbed, to apply these 4 applications that you can see in my background, and to check certain performance parameters. And we checked for inference performance. So do we need more or equal amount of training when compared to centralized training? Or sorry, that's convergence rate. Inference performance is, of course, the performance of making predictions in the end. Do we lose quality compared to centralized training when using split learning? The third one is computational requirements. That's similar to the explanation I just gave about phones being strong or computationally strong edge devices. How much compute would a hospital need to collaborate? Because I'm going to give a big hint, it's going to be lower than doing all the computation on yourself, because part of the network is now centralized. And lastly, we calculate the computational overhead. Because we're sending data around, we want to know if it's feasible to send these large amounts of medical data over. So we can calculate this computational cost by having these 4 problems and computing the size of the features that we're sending over. And we can also compare that to federated learning. I always hear that I lose the half of my audience with the first formula, so we're going to quickly move forward and show some more graphs. This is inference performance, and we can see well, on the top you see inference performance, and you can also show convergence rate. Basically, we try to show if there's any correlation between an increased amount of participating institutions and the performance that we're getting. And for all of these examples, there didn't really seem to be a strong correlation between the two. And so here are the our rows for the results. And lastly, the computational requirements. Because we're now doing part of the training centrally, we can lower computational requirements on the participating institution. The computational cost is relatively high compared to federated learning. You see that in the left column, which is, for example, for the CheckSpert dataset, which was chest X-ray, 350 times higher. But due to the fact that internet speeds are pretty high at hospitals, we expect it actually not to be a bottleneck in the training. So our conclusions are that split learning can train without losing performance, so that's no compromise. It lowers computational requirements for hospitals, and communication, so sending all the data over, is not going to be a hurdle. So now that we've shown that in theory split learning is going to be feasible, our next steps would be to show that it's also practical. Because just having a very controlled environment is easy, but having several hospitals collaborate is actually a next more practical problem. And that was my presentation. I hope you got a bit more excited about split learning, and I wish you a very good day.
Thank you very much. So Slack is open for Q&A, and the replies are going to come in live or maybe offline. All right, so we are moving to the next research talk.
Well,
this is TIPRDC, Task-Independent, Privacy-Respecting Data Crowdsourcing Framework for Deep Learning with Anonymized Intermediate Representations, by Ang Lee, Jia Go, Wandri Yang, Yuran Chen from Duke and Tsinghua University. It's also worth mentioning that this paper won the KDD Best Student Paper Award.
Hi everyone, my name is Ang Lee. I'm a PhD student at Duke University. Today, I'm going to present our work, Task-Independent, Privacy-Respecting Data Crowdsourcing Framework for Deep Learning with Anonymized Intermediate Representations. For today's presentation, first, I will briefly introduce the problem we are targeting and the motivation. Then, I will formally define the problem and elaborate the framework design. After that, I will present the evaluation results. Finally, I will conclude our work. Nowadays, deep learning has achieved amazing success in many applications. Such success of deep learning partially benefits from various large-scale datasets, such as ImageNet, Microsoft Cocoa, Celib-A, and so on. These datasets are often crowdsourced from individual users. However, the raw data crowdsourced from individual users often contain different types of private information. For example, given a face image, it's easy to identify the person's gender, age, and other private information, either by humans or by pre-trained deep learning models. Similarly, we can also infer users' private information from other data modalities, such as text data. Some studies have demonstrated that we can infer the demographic information of users from the tweets by leveraging the power of deep learning. The privacy concerns from users on data sharing will hinder the generation or use of crowdsourcing datasets and lead to the hunger of training data for deep learning applications. Therefore, it's critical to design a data crowdsourcing framework to protect the privacy of the shared data while maintaining the utility for training deep learning models. An obvious and widely adopted solution is to apply representation learning, which can transform the raw data into task-oriented features, and the users only upload the extract features to corresponding data collector, even though transmitting only features are generally more secure than uploading the raw data. Recent developments in model inversion attacks have demonstrated that adversaries can exploit the acquired features to reconstruct the raw image, and hence the person on the raw image can be re-identified from the reconstructed image. In addition, the extracted features can also be utilized by an adversary to infer private attributes, such as gender, age, and so on. To step forward, inspired by the GAN, generative adversarial networks, several adversarial learning approaches have been proposed to learn obfuscated features from the raw data. Unfortunately, those solutions are designed for known primary learning tasks, which limits their applicability in the data crowdsourcing, where the primary learning task may be unknown or changed when training a deep learning model. Then, what is an ideal privacy protection framework for data crowdsourcing? The aforementioned privacy and generalization issues motivate us to design a more general and secure solution. Next, I will elaborate the problem formulation and the framework design. In this work, we propose a task-independent privacy-respecting data crowdsourcing framework with an anonymized intermediate representation. The ultimate goal of this framework is to learn a feature extractor that can hide the privacy information from the features, such that attackers cannot infer protected private attributes, even if they obtain the features in some way. At the same time, we enforce the learned feature extractor to maximally retain the original information embedded in the raw data for primary learning tasks. Please note that we do not require any prior knowledge of the primary learning tasks when training the feature extractor. As the figure shows, participants can locally run the feature extractor and submit only those intermediate representations to the data collector, instead of submitting the raw data. The data collector can then train deep learning models using these collected intermediate representations, but both the data collector and the adversary cannot accurately infer any protected private information. The goal of the feature extractor is twofold. The first one is to make sure the extracted features conveys no private attribute. The other one is to retain as much information of the raw data as possible to maintain the utility for primary learning tasks. As the figure shows, we use X to represent the raw data, Z for the extract features, and U as a protected private attribute. Therefore, in terms of goal 1, we expect the intersection between Z and U can be as small as possible. So we can formulate the goal 1 as minimizing the mutual information between Z and U. And then this optimization problem can be converted to a max-min problem. With regard to the goal 2, we expect the intersection between raw data X and the joint information of Z and U can be as large as possible. As a result, we can formulate the goal 2 as maximizing the mutual information between X and the joint information of Z and U. We would like to refer audience to our paper for more mathematical details. Finally, we can formulate our objective function based on the above two optimization problems. In addition, we also introduce the lambda as a privacy utility budget to balance the trade-off between the utility and the privacy. According to the formulated problem, we designed a hybrid learning method to train the feature extractor. As the top figure shows, there are 3 modules involved in the training process: the feature extractor, the adversary classifier, and the multi-information estimator. In particular, we designed the privacy adversary training algorithm to achieve goal 1, enabling the feature extractor to hide the private attribute from the extracted features. The path algorithm is designed by simulating the game between an adversary who aims to infer private attributes from the extracted features and a defender who aims to protect user privacy. When we simulate an adversary who tries to enhance the accuracy of the adversary classifier as high as possible, the classifier needs to be optimized by minimizing the corresponding loss function. On the contrary, when defending against the private attribute leakage, we train the feature extractor in path that aims to degrade the performance of the classifier. For goal 2, we propose maximize algorithm to make the feature extractor return as much information from the raw data as possible, in order to maintain the high utility of the extract features. Specifically, the JSON-Shannon multi-information estimator is adopted to measure the lower bound of the multi-information. Finally, we can train the feature extractor in an alternative way. In particular, within each training batch, we first perform path algorithm and the maximize algorithm to update psi and omega, respectively. Then, the feature extractor will be updated according to our defined objective function. Next, I will show you our evaluation result. We implement our framework using PyTorch and perform the training and the testing on our server with 4 powerful NVIDIA GPUs. We adopt 2 image datasets, SLDML and LFW, and 1 text dataset collected from Twitter for training and testing. In addition, we compared our method with 4 privacy-preserving baselines, which have been widely applied in the literature. The noisy method perturbs the raw data by adding Gaussian noise. The DP method means applying the differential privacy, where we inject the Laplacian noise in the raw data. The encoder is a basic DNA-based encoder to learn latent representation, and it holds the same model architecture as the feature extractor in our framework. The hybrid method applies PCA to the extract features from the above encoder, and then add Laplacian noise to those compressed features. First, we evaluate our method on 2 image datasets, SLDML and LFW, and we compare the utility privacy trade-off of our method with 4 baselines. In this experiment, we set young and gender as the private attributes to protect in SLDML, and consider detecting gray hair and smiling as the primary learning tasks to evaluate the utility. With regard to LFW dataset, we set gender and Asian as the private attributes, and choose recognizing black hair and eyeglass as the classification tasks. Here, we evaluate our method with 4 options of lambda, which are 1, 0.9, 0.5, and 0. Ideally, we expect that the accuracy of primary learning tasks can be as high as possible, but can decrease the accuracy of private attributes to a random guessing level. For example, in terms of a binary private attribute, we hope the accuracy of it can be reduced to 50%. As the figure illustrates, although our method cannot always outperform the baselines in both utility and privacy, it still achieves the best utility-privacy trade-off under most experiment settings. For example, as shown in this figure, our method achieves the best trade-off by setting lambda as 0.9. In particular, the classification accuracy of Asian on LFW is about 55%, and the accuracy of eyeglass is 86%. This demonstrates that our method can effectively protect privacy while maintaining the high utility of the extract features. An important step in the hybrid learning method is to determine the utility privacy budget lambda. We also evaluate the utility privacy trade-off by setting different lambda. The top row figures show 3 evaluations on SLDML. We can find that the classification accuracy of primary learning tasks will increase with a smaller lambda, but the privacy protection will be weakened. Such a phenomenon is reasonable, since the smaller lambda means hiding less privacy information in features, but returning more original information from the raw data, according to our defined objective function. We further visualize how different options of lambda influence the utility maintained by the learned feature extractor. This is done by training a decoder with the reversed architecture of the feature extractor. And then the decoder aims to reconstruct the raw image by taking the extracted features as input. Here, we set gender as the protected attribute when training the feature extractor. At the bottom row, The figure shows decreasing lambda allows a more informative image to be reconstructed. This means more information is retained in the extracted features with a smaller lambda, which is consistent with the result shown in top row figures. We also refer the audience to our paper for more detailed experiment result. Since we usually train the feature extractor before collecting the data from users, the transferability of the feature extractor also determines the usability of our method. We evaluate the transferability of our method by performing the cross-dataset evaluations. In particular, we train the feature extractor using either SLDML or LFW, and then test the utility privacy trade-off on the other dataset. As the table shows, the feature extractor that is trained using one dataset can still effectively defend against the private attribute leakage on the other dataset, while maintaining the classification accuracy of the primary learning task. For example, if we train the feature extractor using SLDML and then test it on LFW, the accuracy of gender decreases by 1% compared with directly training the feature extractor using LFW. The accuracy of black hair marginally increases by 1%. The reason is that the SLDML offers a larger number of training data so that the feature extractor can be trained for a better performance. We also evaluate our method on dial, which is a text dataset consists of tweets. Here, we choose race as a private attribute to be protected, and predicting mentioned as a primary learning task. Similar to the experiment settings in SLDML and LFW, we evaluate the utility privacy trade-off on dial by setting different lambda. And the figure shows the classification accuracy of the primary learning task will increase with a smaller lambda, but the privacy protection will be weakened, showing the same phenomenon as the evaluations on image datasets. To conclude our work, the feature extractor is learned to hide privacy information in features and maximally retain original information from the raw data. By applying our method, a user can locally extract features from the raw data using the learn feature extractor, and then transmit the features only. Evaluations demonstrate our method attains a better privacy utility trade-off than existing solutions, and a good transferability across datasets. Thank you for your attention. We refer audience to our paper for more details. Please let us know if you have any questions. Thank you.
Thank you, Ang Lee, for the wonderful talk. I see one question is, does the adversaries in your approach also have access to the labels?
Yeah, actually, this is a good question. So we assume the adversary can use his own data to collect the training data. I mean, once the user has a pre-trained feature extractor, the adversary can feed his own data to the feature extractor and collect the representations for the training. Yeah, actually, the answer is yes. The adversary has a label for the training data.
Got it. Yeah, thank you.
Yeah.
So any more questions might show up on Slack, and I guess you can engage offline as they come up. So yeah, thank you very much for your talk. So we move on to the next talk now.
Yes, thank you.
Hi, everyone.
Okay, so we have a break. Let's see. There's a lot on the schedule just to remember. So yeah, so the break is for 20 minutes till 3 p.m. And then we have a few more research talks. And then there's a hands-on training workshop for the third part, Code Your Own SL, module 3. And then there's a closing remarks and some discussion and social. This is mostly a discussion on social than remarks, actually. All right, so we'll be back at 3 p.m. EST, 20 minutes from now. All right, we're back from the break. So now is the last leg of a few more research talks. And then we have the Code Your Split Learning hands-on coding session and tutorial for module 3. We did modules 1 and 2 yesterday. So there's the Slack channel. Moving on to the next talk. So we now have a split fed, blending federated learning and split learning by Chandra Thapa, MEP Chamikara, and Said Kemte from CSIRO Data 61, Australia.
Hello all, I am Chandra Thapa from CSIRO Data 61, Australia. Firstly, I'd like to thank Pranit for organizing this nice workshop and giving me an opportunity to share our works with you all. It's been a while working on distributed collaborative machine learning, including federated learning and most especially split learning. And I'm more than happy today to share our works on a split fed that blends the federated learning and split learning. This joint work with MEP Chamikara and Said Kemte, both from Data 61 CSIRO. Besides, I will highlight our results on separate works, which is an evaluation of federated learning, especially the federated averaging and split learning for the Internet of Things. So this is separate work and joint work with the Yasun Gao and team within the CSIRO and SKU University, South Korea. This is the content for today's talk. I'll start from introduction of split fed learning, then discuss the default privacy in this learning. Then we go to add more privacy in the framework, present some experimental results, including the performance of federated learning and split learning in the Raspberry Pi implementation, and conclude by highlighting the challenges and open problems in the split fed learning. As we know, in a split kind of learning, we have a full network. Network here means the model. Then the first step is to split the model into multiple portions. In a very simple setup, we split into the two portions. One is client-side model portion, and the second one is server-side model portion. Now, this is our distributed setup. As for an example, 3 clients with their local data and 1 main server, and ready to perform distributed machine learning collaboratively. We send the client-side model to all the clients and server-side model to the main server. Now the training in the split-fed learning happens as follows. Each client performs the forward propagation of their client-side models independently and in parallel. This is opposed to the split learning, where sequential training happens across the clients, which force the clients to be idle as it needs to wait the other clients to finish its training with the server. Then they send this mass data to the main server. After receiving this mass data from the clients, main server starts forward propagation on the server-side model separately for each client. So we can assume this can happen in the parallel, but in our implementation, we did it by multi-thread programming. Then in the back propagation, else the gradients of this mass data, and then these are the respective gradients are transmitted back to the clients. Upon receiving the gradients of these mass data, each client performs the back propagation, and this completes the one forward-backward propagation. And we say it one global epoch if all the local data are considered. Now, how to maintain the model synchronization? So we can start from the server side, motivated from the weighted averaging. We perform the weighted averaging and make the server side global model. But now, how about the client side? So we introduce a fed server, which is responsible for the client side model averaging. That is again the weighted averaging. So client sends the models or the model gradients, and fed server sends back the global model or global gradients. The main server can be fed server here, but in this case, all the operations must perform in the encrypted form, something like homomorphic encryption, and which does not allow the main server to learn anything about the client-side model updates. But for simplicity, we keep the separate fed server at the client side. The training happens as described, and we call this approach the split fed version 1. Why version 1? We now go to this point. The question here is, do we really require to perform weighted averaging to the server-side models? And the answer seems not. So we have an alternative way. This is what's happening in the split-fed learning. How about keeping the only one copy of the model at the server side? Let's say this. First, all the clients send this mesh data to the server. Server starts forward propagation on the client's one is mesh data, and then sends the back propagation, and then sends back the guidance to the client one. Then the updated model starts forward propagation to the client's two mesh data, and so on. This is what we call the split weight version 2. So far, we see the split weight learning approaches. Now let's discuss the default privacy in this learning. We know this is a model to data approach. We send the models to the clients or the data custodians rather than pulling out the data out of them. So this maintains a level of privacy and data control limits within the data custodians. So the next point is obvious, that is the model privacy that we obtain from the network split. Client and server doesn't know about the updates of their side, and difficult for them to guess if properly designed network, then it is not even possible. There are still rooms for the information leakage. Firstly, it is during the client-side model synchronization. Each client will receive the global client-side model. And how we tackle to this issue is we do this by applying the differential privacy measures at the client-side model training based on the approach developed by Abadi. Secondly, there can be the client to main server leakage from this mesh data. How we tackle this issue is by applying the calibrated noise generated based on the Laplace distribution to this mesh data. And we have not done more analysis on this part, but we can argue that mighty version of this mesh data enables more privacy than the original mesh data. Now it's the time to see some experimental results. So the experimental setup is IID case in our scenario. So that means equal number of uniformly distributed samples in each client. These are test convergence curves for federated, split, and split fed version for various number of users. For this data set, that means the HAM 10,000 data set, and then the model, that is ResNet 18, the performance is not affected by the number of users of 200. But in other experiments, for example, Linet 5 on FMNST, higher user means slower in convergence. So in another separate experiments with LXNet on HAM 10,000 with the 100 users, we have something different observation. That is, test accuracy sharply fell around 20% after 20 epochs, both in split and split weight version 2. We are others stay around 60. So here we see the model and data dependency in the test performance. As the main motivation of the split fed is to decrease the training testing time, we have done the theoretical analysis in the paper, and this is what we observe in our experiments. We see 4 to 6 times faster training time for the split fed version than the split learning if you go for experiments with 5 or more clients. The right figure is what we have after applying the privacy measures, that is differential privacy, client-side model training, and sending the noisy mesh data. So more than noise means the slower in convergence, and this is what we expect. In this slide, we are talking about our separate work where we implemented split learning and federated learning on Raspberry Pi kits, so to see their performance. So our performance metrics are training time, memory usage, power consumption, temperature, and communication overhead. So in our experiments, we found that bigger models and data sets are challenging in terms of computation and time for the IoTs. So we limit our detailed observations and choose the 1D CNN model with the first 2 layers running on the Raspberry Pis and ECG dataset. For the time over, as sequential training among the clients have higher than the federated learning. For the communication, again, the federated has negligible overhead to the split learning, all due to the data size dependency of the split learning. More data means the higher communication between the client and server during the training in the split learning. For the peak power and temperature, we can see the advantage of split learning to allow running few layers at the client side. Its peak power and temperature is lower than the federated learning. So these metrics have high importance in the practical settings. For more results, please see the reference. This is my last slide. So we have one book chapter that reviews the current activities in the split learning space available on the archive, and we mentioned these challenges and open problems there as well. So as we know, it is challenging task to find the correct layer in split kind of learning, which includes the split fed learning, such that we minimize the leakage and computations at the client side. So it is still an interesting problem. Now going into the next point. So for the non-IID case, extreme case will be the single class problem. That means each client has only one class of dataset. Split and split fate approaches doesn't work appropriately for some dataset, and we are in our observations with the swell condition dataset, it doesn't learn at all. So that's another future avenue. As the split enables the machine learning on the resource constrained environments such as IoT, communication efficiency is another important issue. So we need to look into this direction as well. Last but not least, studies on the various attack scenario and split learning is another potential research direction. So we need more studies to make the split learning robust here. And this concludes my talk today. Thank you very much.
Thank you very much, Chandra Thapa. We have questions coming in. That was a good talk. The question, what metrics are most important in the design choice for split-fed learning from a computation and communication efficiency point of view?
Thank you, Pranit, and thank you for the question. So I think to answer this question again, it depends on the our application. So if we think about the Raspberry Pi and the IoT, the end, then again, as I also mentioned during the presentation, that going for the even for the two-dimensional convolutional neural network-based architecture, it's very difficult to run on the IoT gateways such as Raspberry Pi. So again, it matters. And the benefits that we can leverage from the split learning again is the running the few layers on these computational resources, the devices. On the other hand, if you go into the this cross-silo type of setup, like in the federated learning, which where the large organizations, which we can assume the higher computations, then we can go for the the higher data set size. We can think about the bigger models. And I think this addressed something from the computation side. And then for the communication efficiency point of view, if we think again, it matters the what's the size of the activations or the the dimension of the layers of the COT layer. That's especially the COT layer. Yep, and then in our paper we have assumed that all the all the communications, these channels, and then the number of users always communicate with the server. But again, we can think about the asynchronous kind of connections where the dropout can happen, and then the this is still it's ongoing, and we haven't done that. But in our paper we have not considered that means these drop in communication and other sort of things. And I'll update more on the Slacks if any other questions.
Sure, yeah, sounds great. Yeah, we'll have more questions on Slack. Yeah, this is great. Thank you very much.
Thank you.
Good afternoon. My name is Hannah Wisnett, and I recently received my master's.
All right, so we have our next talk. This is split learning on FPGAs, as well as on what is known as FPIAs that are coming up for field programmable imaging arrays. This is a talk by Hannah with joint work with myself and Ramesh. Hannah was a visiting student at our group and was a technology and policy student in MIT from the US military.
Good afternoon. My name is Hannah Wisnett, and I recently received my master's degree from the Technology and Policy program here at MIT, where I was also a military fellow at Lincoln Laboratory. And today I'm going to be presenting to you on my research topic, which was split learning applications on FPGAs. To start with an overview of what I'm going to be talking about, I'm first going to give an introduction to the group I was working with at MIT Lincoln Laboratory, the Advanced Imager Technology Group, give a little bit of overview on my research and what motivated it, share some background on FPGAs themselves, the technology, and why they're important and why they're useful. Then talk a little bit about simulation I did of potential machine learning algorithms, and specifically split learning algorithms on FPGAs, and the results that we got from those simulations. Then talk a little bit about the use cases I think that this will have, and some future work that needs to be done to make split learning on FPGAs a reality. To start with an introduction to the Advanced Imager Technology Group, the group that I worked with over the 2 years that I completed my master's thesis. That's a group at MIT Lincoln Laboratory that focuses on designing and fabricating imagers for powerful cameras and telescopes that have both scientific and defense applications. So that really covers a broad range of technologies. A couple of examples that I have up there are single photon sensitive images for LiDAR. The image you see up there is actually a scan of the city of Boston that they took using imagers developed at Group 87. They've also developed charge-coupled devices, imagers based on those for use on the OSIRIS-REx satellite. Now, the specific project I worked on at MIT Lincoln Laboratory is called Reimagine. Reimagine is a DARPA project that was imagined as a single, multifunctional imaging platform that can accommodate multiple modes of operation and interface with multiple types of imaging sensor. Ultimately, it's intended to be able to autonomously toggle between different modes of operation using machine learning algorithms. However, FPGA-based developers face a lot of resource constraints and design difficulties that developers working with more typical CPUs and GPUs do not. So through Reimagine, MIT Lincoln Laboratory has prototyped the first, what they refer to as the Field Programmable Imaging Array, an FPGA-based imager. This has a lot of advantages over sort of typical single-use imaging platforms that are previously deployed. These include that the cost of fabrication is amortized over multiple programs. You can add new capabilities to already fielded systems just by pushing software upgrades. And also that it can support a variety of detector types that all interface with a common digital backend. So these detector types might be designed and used by industry, but interface with the base hardware, what's shown as Tier 1 on the image here, which is what's under development at Lincoln Laboratory. So in working with both Lincoln Laboratory and the camera culture group here at MIT, we had a few motivating questions that we wanted to answer with my research. The first of this being, is it even technically feasible to implement split learning applications on FPGAs? The second, examining how developments in FPGA technology have changed the landscape and potential for FPGAs as platforms for sensor systems, and also for new machine learning applications. And the third question we wanted to answer was what current and future use cases might exist for the implementation of split learning on FPGAs. Before I answer these questions, though, I want to give a little bit more background on FPGAs, or field programmable gate arrays, for those people who might not be as familiar with them. FPGAs at heart are really, really simple. They're just a series of logic blocks arranged in basically a grid that are connected by interconnects and surrounded by input and output blocks that can be used to implement basically any computer program that exists. So you can compare them pretty easily to either CPUs or GPUs, that kind of computing technology, or to ASICs or application-specific integrated circuits. These three technologies kind of exist along a spectrum, and all three of them are used really commonly. And I like to think of FPGAs as a happy medium between the other two. CPUs benefit from having a really, really fast design cycle, whereas ASICs are very specific and take a long time to develop. FPGAs are somewhere in the middle of that. CPUs and GPUs, like FPGAs, are really flexible and can be used for anything. ASICs have very specific and limited applications. From CPUs and GPUs, you don't get very good performance, whereas from ASICs, you get really, really good performance because these technologies are optimized to do whatever they're doing and do it well. FPGAs are somewhere in the middle between the two. They can be optimized a little bit better than CPUs and GPUs, but they're never going to reach the performance levels of ASICs. Same thing with power. CPUs are more power intensive, where ASICs are less. FPGAs are in the middle. And the one area where FPGAs really are not quite as strong as CPUs or as ASICs are programmability. There are a lot of very well-articulated high-level languages that programmers working on CPUs and GPUs can use. And since ASICs don't do very much, they have these very specialized programming platforms that their developers can use. FPGA developers do suffer a little bit from having a much more difficult technology to program, with fewer tools that exist to help programmers along, although, as I'm going to talk about, that's changing really very quickly. Okay, so you might be asking yourself, if FPGAs are so great, if you can do whatever you want on them, why is there any question about whether or not we can do machine learning on FPGAs? And it really comes down to a couple of things. The first one being resource constraints. FPGAs simply don't have as much I/O, not as much access to memory as more general purpose processors like CPUs and GPUs do. They also have much longer development cycles compared to general purpose processors, and much higher domain-specific knowledge requirements. If you take somebody who's done a ton of programming in C or Python or whatever language you want, that person is going to have a much harder time writing applications for FPGAs than they are transitioning to a new high-level language for use on CPUs or GPUs. But we do want to take advantage of the FPGA-specific advantages that they offer. One of these being the amount of optimization you can do and the amount of flexibility that you have is actually higher on FPGAs than it is on CPUs and GPUs. You can get performance improvements. FPGAs are highly parallelizable, and you can make things go really, really fast, basically, using not very much power, which is important for certain applications. And the third advantage is that there are a number of high-level synthesis tools under development that basically overcome the domain-specific knowledge requirements that are such a disadvantage. This is a really quickly growing field. Since I finished up my thesis in September, the major tools for this have had a lot of upgrades released, and the communities using them have gotten bigger and bigger. But already we do see certain implementations of machine learning on FPGAs out in the wild. They're mostly used to supplement GPUs and accelerate convolutional neural networks because, like I said, they're highly parallelizable and there are certain tasks that they can do really, really well if they're freed from typical I/O and memory requirements. But people want to do more. People want to have the ability to implement more of and more machine learning algorithms on FPGAs. And to do that, there are a lot of high-level synthesis tools under development. A couple of them are listed above. These are sort of the most notable, most active ones right now. One is Vitis AI, which is under development by Xilinx, one of the major FPGA vendors. It's being released basically in concert with their typical Vivado FPGA programming package. And the one I ended up using is HLS for ML, which is just a Python package. It's available for free to anyone, and it converts either PyTorch or Keras or other sort of higher level machine learning model descriptions all the way to HLS files that can be used by Vivado HLS to generate a bit stream that can be loaded directly onto an FPGA and used to start conducting inference or training. So how that works is the description of the neural net as well as the specifications of the target FPGA are provided by the deep learning expert, by whoever is writing this algorithm. This example is from FPGA ConvNet, that project. But basically it goes through and parses and optimizes those specifications as well as the model description in order to generate high-level synthesis files, which are then given directly to Vivado HLS or a similar tool provided by the FPGA vendor, which are then converted to a bit stream that can be loaded onto the device. So as a part of my research, I went through and I tried this. So I'm going to present to you guys the workflow that I used for simulation of split learning algorithms on FPGAs. When I did this, I selected a very simple client-side split learning model. You can kind of see to the right, it doesn't have very many layers. The layers themselves aren't very large. This was mostly to avoid time constraints. I could run this over and over again and try different things without it taking too long. I used HLS for ML, and my target FPGA was a Kintex UltraScale 115. This is an FPGA I selected because it has similar specifications to the Reimagine project at Lincoln Laboratory. It's not exactly the same, but it gave me a good sense of whether or not the model that I generated would be able to be implemented actually on the FPGA based on its resource constraints. So I went through, I trained the model just on the MNIST digit recognition data set on my laptop, converted that model to a Keras model, which is basically just a .h5 file with all the weights of the model represented, and a JSON describing the overall model architecture, which you can see on the left. I put it through the HLS for ML package, which gave me an intermediate C++ representation that you can see on the top right. This is the part that's a little bit difficult for the programmer to generate by themselves. There's a lot of C++ packages, tools, libraries, things like that you can't use if you're feeding them into Vivado HLS and trying to get a functional FPGA bit stream out the other side. But if you use what's given to you by HLS for ML, you can just feed that into Vivado HLS and allow synthesized FPGA code to come out, which is then converted into a bit stream and loaded onto a specific device. The good news with this is it worked. We were able to go through and successfully classify images on an FPGA using a split learning model. What you're looking at here is some screenshots from the Vivado synthesis report that give you a sense of how many of the lookup tables, how many of the I/O blocks, how many of the DSP tiles within the FPGA were used in doing this. And you can see that the resource utilizations are not low. You're using somewhere around 90% of the I/O block, you're using about 60% of the DSP tiles. But the good news is that this is not a very optimized version. There's a lot of pruning of the model that can be done. There's a lot of reuse of resources that can be done. There are a lot of sort of different implementations you can use to limit the amount of I/O that you're using in order to successfully implement this on Reimagine or a similar Reimagine type project. So what this sort of simple example showed us is that split learning on FPGAs is indeed possible, and it might be desirable if an implementation needs to take advantage of some of the other advantages of FPGAs that I saw as I was doing my survey with my research. There are a number of things that FPGAs have to offer in terms of security and privacy. There's a lot that they have to offer in terms of performance and power usage, and there's often a lot that they have to offer in terms of the economics of implementing this stuff. They're already widely used in sensor systems where things like reconfigurability, the ability to have multiple functions is at a premium. So some of the areas where this might be really useful is, first of all, healthcare, where there's a high value on privacy concerns. I didn't get into it that much in this specific presentation, but FPGAs have certain privacy tools that are really useful for protecting that stuff. Another area is particle physics and ultrafast astronomy. This is an area where there's a really high value on low latency, which is an important part of what FPGAs have to offer, and also where there are existing resource constraints. And finally, in defense, obviously a place where you might value low latency, reconfigurability in multiple uses, as well as low power usage for stuff that's out in the field. So overall, this is a really exciting area. Like I said, these high-level synthesis tools are changing really rapidly. They continue to expand their capabilities and the ease of use of their interfaces. A lot of future work in this area, I think, is available to be done. For example, benchmarking different amounts of resource utilization that could allow developers to understand the complexity of models that they'll be able to implement on specific FPGAs. As well as the development of programming toolsets specific to programs like Reimagine that have their own programming platforms, and potentially the analysis of bandwidth limitations that may favor different distributed machine learning algorithms like split learning. So thank you very much to everyone for listening to my presentation. Thank you to the Camera Culture group at the Media Lab for having me back. And I hope everyone has a great rest of the workshop.
All right, that was a very useful talk on split learning on FPGAs. So Hannah has graduated and she is not available in live online right now, but she will certainly be available for questions offline. If you ask them in Slack, she will get back to you. So we are moving to our next talk. So this is more of a case study from NTT Data. It's a preliminary assessment of federated ML for fraud detection. This is the last talk of the workshop event. We're going to have a hands-on code your own split learning hands-on coding session and a tutorial for module 3 after this. And then there's going to be an open discussion and social for a few more minutes after that, and that will be the conclusion of the event.
Welcome to this presentation, a preliminary assessment of federated machine learning for fraud detection. This work has been carried out by NTT Data Italy. NTT Data, part of the NTT Group, is one of the most important IT services provider operating in more than 50 countries. And thanks to the Center of Excellence for Artificial Intelligence, NTT Data aims to become a global strategic partner for customers in AI adoption and digital transformation. The project that we carried out is about fraud detection, known as one of the most urgent cases for the financial sector. It has been estimated that around 30 million euros per year are involved in fraudulent transactions in Italy alone. Machine learning can give us a precious help in fighting this phenomenon, as it is expected to be able to increase the current detection rate by 15%. The Italian banking market is one of the most fragmented in the world, making it difficult to exploit the knowledge of the data. In fact, everyday banks face challenges that would be better faced together. There are some applications, however, that may require to share data, and this might not be possible due to privacy and security constraints. Federated machine learning is the technology that enables a non-competitive collaborations among multiple banks, and moreover, it allows the application of collaborative AI at scale with no fear or need of sharing private data, leading also to the creation of new business models. There are also multiple key benefits. The most important one is that each bank should not reinvent the wheel, since there would be the same machine learning model for each bank, and they would be not required to build a specific model for each bank. Also, it would be possible to exploit all banks' data knowledge without sharing data and make strategic partnership thanks to the secure ecosystem. Among the possible use cases of federated learning, such as anti-money laundering and credit risk estimation, fraud detection is the one we have chosen for our POC. From these slides on, I'm going to give the words to Ricardo.
Thank you, Federico, for your introduction on federated machine learning. So for this POC, we partnered with a consortium of several banks and companies whose mission is to analyze and promote innovation in the financial sector. And as Federico said before, is one of the most segmented and fragmented one. And the goal is also to encourage the dialogue between banks and innovation partners. For this POC, the scope is that we focused on the tech foundations of the federated learning approach in the context of credit card fraud detection. This work represents a very first but necessary step towards a complete use of this technology. Our goal was to show quantitative results that demonstrate the benefit that each individual bank could obtain by cooperating and collaborating within the federated framework. The dataset that we used is a public one, since our client, of course, since he's a consortium, doesn't have access to transactions data of the banks. But we made sure that this dataset was able to replicate the credit card fraud detection task. Of course, since it's a replication of a real-world scenario, the dataset is highly unbalanced. And to validate this approach, we used Python and also TensorFlow Federated as framework for the federated approach. Regarding the experiment we conducted, we wanted to compare a non-federated and federated approach in a simulated environment. Regarding the data, we split the data. We split the data based on the transactions time in order to have 3 clients, 1 server, presenting statistical differences, and so leading us to a non-IID scenario, which is one of the most common scenarios in the federated world. And then we enrich such data set by employing this multi-technique in order to find the imbalance in the data set. Regarding the non-federated scenario, so the local models have been trained on local data and then tested on each client's test set. While for the federated scenario, we have a global model that was built by a federating approach, and so trained in a federated fashion and then tested on each client's test set. So here we present the workflow of our experiment. So we start by splitting the data according to the time variable to create the non-IID datasets for the 3 clients and the single server. Then each client and of course the server has the dataset enriched by using this multi-technique in order to augment the number of fraudulent transactions. And then our experiment is composed of 2 streams. The first one is the non-federated stream, in which we locally trained each single model, and then we test such models on their testing dataset. While in the federated approach, we train each single model, and then we use the averaging algorithm in order to build the federated model. And so testing, and then we test this federated model we tested this federated model for each testing dataset. Of course, the goal of our experiments is to conduct a performance evaluation that we will explore in the next slides. So regarding the dataset, the dataset originally presented 0.17% of fraudulent transactions, and with Mote, we were able to increase such amount up to 1% of the whole dataset. For the model, we server and clients shared the same fully connected neural network structure that is here in the table. And so as you can see here, the input layer is composed of 29 units, while the hidden layer is composed of 16 units. Finally, we have an output layer, which is composed of a single unit, and it has an active action function, which is the sigmoid one. So for the non-federated scenario, each party's model, so we have 3 clients models and 1 server models, was trained for 100 epochs and tested on its own test dataset. While for the federated scenario, we first trained the server on its training dataset, and then we share the weights of the server model to the clients. After that, we train each client models for 30 epochs, and for 50 rounds, we apply the averaging algorithm in order to build the federated model. So regarding the results that we obtained, since the dataset is highly unbalanced, we focused on the metric, which is the area under the precision recall curve. And as you can see here from the table, the federated model was able to outperform each local model, so for the 3 clients and the server. So these results led us to the following conclusions. The first conclusion is that our assessment validates the capabilities of federated machine learning in the banking sector for the credit card fraud detection task. Also, we noticed that the federated model had better performances compared to a non-federated approach. And so this made us think, and so we strongly believe that such approach, so the federated machine learning approach, could be able to reduce the economic losses from credit card frauds in the Italian financial sector. Finally, this was the team that worked on the project, and here you can find each member email, and if you have any questions or any doubts and you want to discuss about it, please reach us out at the following emails. We are happy to give you some answers. So thank you all for your attention. It was our pleasure to present our project. Thank you again.
All right, thank you for your study and your project at NTT Data, for sharing it with us. I think we have one of the speakers, Ricardo Ismechi, on available live for taking questions as well. The rest of the questions can be taken offline on the split learning Slack channel that you shared. So one quick question I had was, when you talk about the Italian financial sector being highly fragmented, it would be nice if you can explain a little more about what makes it different or unique, or what you were referring to. We don't hear you, Ricardo. but yeah, so this is the speaker room. So there's certainly a Slack channel that is very active with a number of people there. So we can certainly take it offline from there and see what you have to say. Oh, right, go ahead. Yeah, I can hear you.
So can you repeat your question, please?
Yeah, so when you refer to the Italian financial sector being highly fragmented,
yep,
it would be, if you were, I'm kind of interested in understanding a little more what you mean by that.
So what I'm saying is that in our market, in our financial sector, so we have so many banks, and also clients are all over such banks. And so we don't have, let's say, just one, like we don't have like most important banks in Italy. So what I'm saying is that every bank has its own data set and also fraud detection system. And so that's why we think that federated machine learning could help the sector.
Yeah. Got it. Yep, makes sense. Yeah. Yeah, thanks for this wonderful case study and this presentation of this project. We're looking forward to hearing about more industrial applications as well. Federated learning and data.
Yeah, thank you for the possibility. It was our pleasure.
Yeah, thank you. All right, so that brings us to the end of the entire event. We had quite a few wonderful keynote talks and research talks. So moving along, before we go to the hands-on coding tutorial for Code Your Own Split Learning, I'd like to repeat and recollect about this call for survey on advances and challenges in split learning that we all are trying to put together. So we'll be reaching out to the speakers and their co-authors and collaborators in the next few weeks so that we can set up a breakout session to figure out the initial outline of the paper. Once that is done, then we work offline and integrate all the contributions into this large manuscript that we're trying to put together. All right, so we move on to the next hands-on training workshop. This is the module 3. We had module 1 and 2 yesterday. So this is for Code Your Split Learning, and Abhishek Singh will be presenting and taking it from here.
Thank you, Praneeth. So we'll begin the tutorial part 3, and I'll be sharing the notebook in a second with you all.
Sure.
I'm sharing it on Slack. Let's see. Okay, Praneeth, I'm going to share screen, so might want to.
Sounds good. Go for it.
All right, everyone. Welcome to the Split Learning tutorial part 3. And just to set up the scope, we'll be having a brief recap of yesterday's tutorial and discuss things which we broadly covered yesterday. And then focus of this tutorial is around defense techniques for split learning. And we'll start up with the setting up of defense pipeline and then comparing information leakage. And then we will discuss some limitations and also what are some other possibilities in the future. And I've shared the collab notebook link on the Slack. And if you're watching the video from somewhere else, from Zoom or YouTube, then please let us know somehow. And we can share the link there as well. Okay. So yeah, let's begin the recap. So yesterday we started with split learning core idea that we have a client network, server network. We pass the sample X, we get intermediate representation Z, and then we obtain the label Y. And then during the training process, we also communicate gradient back from the server network to the client. And we also discussed information flow in split learning and also reconstruction attacks. So what we discussed in information flow was what all information is processed in the intermediate activations when the sample is passed through multiple layers. And then we saw some reconstruction attack where we were able to reconstruct the image given the sample, given the leaked pairs of sample and corresponding activations. So building on top of that, the natural question is, how do we prevent these reconstruction attacks? So that is the topic for this tutorial. And before we dive deep into the defense, let's revisit the reconstruction we had obtained yesterday. So what we did yesterday was take the training data set, build a data set of training images, activations, and use this data set to train an adversary who is able to reconstruct images from activations. Now here we are visualizing some of the images from the test data set and seeing how well it's able to reconstruct. As you can see, more or less all of the information is visible in the reconstruction. So now question comes, what are the defense techniques which can prevent these reconstructions? For the sake of this tutorial, we'll be considering one category, but just for covering the both aspects, there are informal and semantically driven methods. And the second category is more around formal methods with guarantees. And as I said, focus of this tutorial is around informal methods. And what I mean by informal method is basically we'll be using data-driven methods for defense. And we'll be doing some training of separate network, which could help us in defending the activations. So before we even go to that aspect, let's see what happens if we do the same thing, which we did yesterday, but this time we choose the split layer S7. So if you can recall the architecture, the place where we do the split of the network also helps us in estimating how much information leakage is happening and how well the adversary can reconstruct the image. So yesterday we took an extreme, which is an extreme where it's very difficult for the defender to defend and very easy for our adversary to attack. And that was the split layer 1. So we literally took the output of the first layer and reconstructed the image. But now we are gonna flip the table and basically go to the end of the network and take the last layer and try to reconstruct the image. So we'll basically set up the same pipeline we set up yesterday. So importing libraries and transforms for data loader. And I've clubbed the code together because we are not going deep into the line-by-line code explanation. But of course, if you have any doubts anywhere, please stop me or write the message on the Slack. So here, as you can see, yesterday I had kept this value as 1, but this time it is 7, just to evaluate what happens on the other end when we try to perform the reconstruction attack. And then again, we have same training pipeline. So let's go with it. So now another thing here is since it's gonna take some time to train, we can directly skip to the results because I've already kept them in the notebook. And the way it would work is we'll define the reconstruction loss function here, as you can see. Then the next part is to develop a generative model. If you can remember, what we had done in the last tutorial was use a generative model or a decoder, which will take the activation as input and the input image itself as the output and try to minimize this reconstruction loss, which is L1 error. L1 error in the image space. And then we define the adversary model, and this is how we typically train the attacker. And once the attacker is trained, what we do is we feed the test data loader, basically the test set, and try to reconstruct. So given that we still haven't finished the whole loop, this is how the pipeline looks like. And since right now we are in training mode, the attack mode also takes its own time for training. So I will quickly skip to the results. And this is what it looks like. So this is the first row. The first 2 rows belong to original image. And then reconstruction from activations look like this. And of course, this is not the live result because the code is still running, but I've kept the image which I had run like a few hours ago, just for the sake of quick illustration. But if you're running in parallel with me, you can wait for the code to finish, and then you can see the reconstruction coming on your notebook as well. So as you can see, reconstruction is pretty bad. And also, it depends on what criteria or what threshold are you using to qualify good or bad, but there's not much of information which is being reconstructed here. So that's very good. I think we have kind of solved the information leakage here. Now, there is one more problem. As we saw, we are executing 7 consequent blocks of ResNet 18 on the client side, which means if we actually have to deploy this model, 90% of the computation load is on the client side. And if we are willing to sacrifice that much computation load, then we might as well do the on-device classification. So the question arises, can we do something better, which is in the middle, where computation, privacy, utility, all three are in a reasonable ground. And that's where all the recent and clever defense techniques arise, because we just don't want to achieve very good good reduction in information leakage, but also we also want to do the split at earlier layers where the information leakage is typically high. So going back to that statement, we have 3 broad categories of defenses, which allow us to do the split at earlier layers and still give some level of protection against reconstruction attacks. So first category is adding noise to Z. The second category is modeling the whole training scheme as an adversarial objective, where prediction and reason is modeled as min-max optimization task for the client network. And the third category is learning some kind of masking approach on Z, such that a good amount of information is not sent from the Z, but only certain bits and pieces of information is sent from Z to the server side. And all 3 categories provide utility because there is some notion of invariance here. And what I mean by invariance is loosely this. So given that all pixels in the image are not really contributing to the task, what we are sending is a some compressed representation where many pixels have been removed, and removed in such a way that your utility is still invariant. The target task is still invariant to those pixels in some sense. And of course, that's not a formal definition of what I mean by invariance here, but that's the underlying idea to prevent reconstruction while at the same time gives some good utility. Also, these 3 broad categories of defenses is not an exhaustive list. So there are many unique methods. Sometimes they are trying to combine one of these 3, 2 of these 3 or more. And many of the talks in this workshop have been around this idea that how do you build better defense techniques? So the one talk I presented yesterday, Disco, was around that idea, where I was doing something around point 3, learning masking approaches. Then Shredder was presented also yesterday, which is combining 1 and 2 in such a way that the noise model can be learned itself and then applied on the activation Z. And similarly, other techniques also have been leveraging this idea. So focus of this work is around adversarial technique, which is the second bullet point here. 1 second. Seems like my computer is hanged. Let's see. Oh, I see. So in adversarial defense techniques, what we have is another set of network, which is called proxy adversary network here. And what we do, we take the client network, we get the activation Z. And here the goal is to reconstruct the image using a proxy adversary network. And the reason we are calling it proxy adversary network is because we do not really know what is the real adversary network gonna be. So what we are basically doing is simulating an adversary which is closest to the real world adversary. And ideally, from a privacy standpoint, you would like to build an adversary which is the strongest one. But of course, as I had said, these are not formal methods and more semantically driven, and hence we are just trying to learn a proxy adversary instead of designing the worst case adversary. And then, like typical split learning, we still have client network, server network, and we have our typical minimization of loss over the inputs and the labels. But in addition to that, we are adding an additional objective, which is to maximize the reconstruction loss from a client network standpoint. So the way client network will be doing its backpropagation will be based on how well the proxy adversary network is able to reconstruct the image. However, proxy adversary network is not maximizing its loss, just to be clear. It's still minimizing its loss because it's trying to simulate the best possible adversary. So given the data we have, which is activations and images, that is the best it can do. So it is doing its standard empirical risk minimization. All right, so let's see where is our training going on right now. So yeah, we have trained roughly 26 epochs. So we can perhaps stop the training here. And remember, this is again going back to the idea of performing reconstruction attack on the last bit layer. So just for the sake of it, I will now run the evaluation. In evaluation, we are not training any client or server network anymore. We are just training the adversary. And in order to train the adversary, we need activations. And that's why we have this line, which is obtaining activation from the client model. So we'll wait for a few epochs to complete, and then we will try to visualize the result. And probably it should look something like this, what we have here. So going back to adversarial training. And also, if you are familiar with GANs or even adversarial training for robustness in adversarial attacks, this might look very familiar because a similar idea is employed there also. Another thing important here is, which is very specific to defense technique which deploy adversarial training, is that sometimes this adversarial training can be very unstable. And the reason for that is due to these two objectives which are competing against each other, where server network is trying to do best in utility and adversary network is trying to do best in reconstruction. And the client network who is trying to maximize the loss for adversary. So sometimes what happens is the reconstruction turns out to be pretty good because the loss was unstable and training did not go well, but that's something which is which should be subjected to hyperparameter tuning more. So we have the same adversary generative model again, and this time, for the sake of evaluation, we are using something in the middle. So we have the input, we have the split layer as one, and then we had split layer as the last split layer. And now what we are trying to do is basically do something in the middle. So what we are going to do is select split layer as 4, so that it's not very easy to defend, but at the same time, it's not very easy to attack also. So somewhere in the middle. And then we do the adversarial training, and we run for given number of epochs. So before we start this training, we need to see how the reconstruction happened for the previous network, which is still going on. So given we have a few minutes left still, I can just jump to the results again, because this time also, like previous time, I have the results already. So you see the training happening here with losses. And also you can see another interesting thing here, which is that you have the task loss and adversarial loss. And adversarial loss refers to the reconstruction loss we have discussed before, which is measured by L1 error in the image space. For the evaluation, we go again with the construction of a data set of activations and images, and we do a supervised training of decoder. And once the decoder training is complete, we can generate the results. And here I have pre-computed the results again a few hours before. So if you are running live with me, it wouldn't come yet. So probably I can just show. So here are the results. And this is the original. And then this is the reconstruction of the activations. And this is a reconstruction of activations when we had employed adversarial loss. So in terms of qualitative comparison, it depends on what is the threshold again. So for some threshold, it might appear to be defending against adversarial reconstruction, but at the same time not. So again, depends on what threshold you use. But there is clearly some reduction of information leakage, at least from adversary standpoint, because for instance, if you see the figure 4, column 4 in the row 1, there is some red line about the text present here, but in the reconstruction with adversarial loss, there is no such red line. And similar examples can be found on other images also. So overall, that's pretty much it for the reconstruction attacks and defenses. And as I said, there are much more sophisticated defense techniques which are out there, which can be employed, but this is like one of the simplest yet effective, one of the effective defense technique. The idea is to use adversarial learning such that some sort of invariant learning can happen. And another point which is not mentioned in detail here is about the utility. So right now we are only seeing results on the reconstruction and adversarial loss. But another metric to consider when evaluating such techniques is the utility, because we don't just want to see how much reconstruction can be avoided, but at the same time, how much utility we lose when we do such reconstructions. And this can be formulated as a Pareto optimal frontier based on whatever metrics are you using for defining information leakage. And you want as close to be this optimal frontier as possible. And based on that, defense techniques are built around. So yeah, that's pretty much it. And of course, please feel free to add any questions on Slack. But I'm guessing for the sake of this tutorial, we will have one reconstruction completed, so we can see evaluation live as the training finishes.
Great. Yeah. One question on one more. As you said, there are many attack settings and ways to do it. So one is the deep image prior based attack that you talk about. Can you explain what setting that attack would fall under?
Yeah. So deep image prior is a paper in computer vision community, and it has shown that you do not need a lot of activation and images pair to reconstruct the images, because if you know only the weights of the client network, so let's go back to this diagram again. Oops, yes. So here, as I was describing the attack scheme before, we can take the activation and image pairs and train a decoder. But as you can imagine, the decoder would require a lot of samples in order to generate the image effectively. However, in the attack schemes where such a supervised data set is not available, there is an alternate scheme which we are calling deep image prior, because it's derived from deep image prior paper, which was in, I think, 2016. And the idea in that paper is something like this. So you have a network, client network, whose weights are known, but you do not have any data set of activations and image pairs. So what you do is you take the client network and you try to optimize the image in the network space. So you train a separate generative model, which is being trained to maximize the activation given the client network. So it's more like, instead of optimizing a parametric model, we are optimizing image itself. So we start with a randomly initialized image and a randomly initialized network. And since we cannot do any training, we just try to overfit on the activation and see if we can generate the actual image. And it turns out, so the results are much better in terms of qualitative comparison when we perform this deep image prior style attack. And they actually look better in qualitative reconstruction and also on the quantitative metrics we can use for comparing two images. And yeah, just to be sure, like a very broad level answer would be that we use deep image prior kind of attacks when there is no leaked pair of activations and images, and only the client network weights are known.
Very cool. Yeah, that's also very relevant. If there is maybe peer-to-peer weight sharing between clients, for example.
Mm-hmm. So I think probably I can stop the training of adversary and just let's see how the results look like. Of course, it might have been slightly better because it hasn't converged yet, although it is kind of getting towards convergence, but let's see. So this is what results look like when we take the last split layer for, and this is Cypher 10 dataset. So sometimes reconstruction quality also depend upon the image dataset itself you're using. And here you could argue that more or less majority of the information is not visible in the reconstruction. So the proxy adversary we are using is not really able to reconstruct quite well.
Do you think, even in the extreme setting where most of the layers are with the client, but still the technique is guaranteeing to at least empirically prevent these leakage in a very good form at that point? But even in that case, if there are many clients and there's say only one or two layers on the server, like minor processing on the server, even there is still some applied benefit if the compute can be, if there was many clients, that is, or like few clients that is pulling in a lot of data, or many clients pulling a little bit of data that ends up being a lot of data. Do you think those two layers at the server will still do better in the distributed setting than them being by themselves and doing on-device training?
Yeah. And I think, so first of all, yeah, that's a great question. And I think there are three big motivations for doing distributed inference, what we are referring here. So one which is known in the whole community is basically getting some level of basically privacy in comparison to sending the raw data directly. But then you could argue that why not do on-device computation, because anyway, you have to execute a lot of layers on device. And the answer to that is that there are instances where on-device is not possible. The first one is the computation load, of course, where you cannot execute multiple layers. But there are other two places also where on-device execution is not possible. The second is the place where the server part of the model is an intellectual property or some sort of secret model. So server is not willing to share their secret part of the model, but only some pre-processing layers on the client side. So that's one use case where server does not want to share their part of model, and hence there is this notion of called collaborative inference, because client and server are collaborating such that privacy of client data is not lost. At the same time, secrecy of model is not lost from the server. And the third category is more around multitask learning, multitask inference, where the client does not know what all prediction server wants to do. So he just wants to send the activations and see whatever server wants to do, they can do. And it's not just multitask learning, it could be also something like vertically partitioned learning, where you have activations coming from multiple sources and those activations are combined and then the result is being obtained. And I think so these two categories are also very potentially practical for arguing the use case for split inference.
Very cool.
And yeah, for those who were executing the notebook in parallel with me, you can start with the next notebooks, the next cells, where we actually start the adversarial training. So before we finish it off, I'll just start the training so that people who are following with me can run it themselves and see it happening in action. So that's pretty much it. And please feel free to send any questions on Slack. I'll be there. And thank you for attending the tutorial.
Awesome. And these recordings would be available on the live stream from tomorrow as well. So feel free to reach out to us if you need access to the Slack, the Colab notebooks or something like that. Great. Okay, so let me get back to my screen. All right, that brings it to the end. Quick announcements. We will reach out back to you after a few weeks regarding the advances and open problems or like challenges in split learning to be able to put together an outline for what the survey would be. So we'll reach out to all the speakers, their co-authors, and some of their collaborators. Once we figure out what the outline is in some breakout session, after some back and forth after a few weeks, then we can work offline, and then myself, Abhishek, and rest of the people in here can help integrate it into a common overlay file as we go along. So we're looking forward to see how this manuscript will shape up. And that brings us to the end of the whole event. So thank you, everyone. This was fantastic. We're going to be having kind of like a social or like just an open office kind of thing from 4:15 p.m. starting in a couple minutes till 5. So we'll just remain in the Zoom call if there is someone else who would like to join and interact. Thank you. So I'm stopping the live stream.